The lesson today is Oscillations, chapter 19. This is about simple harmonic motion. After this chapter, you should be able to give examples of free and forced oscillations. Use appropriate terminology to describe oscillations. Use the equation A is equal to minus omega squared x to find simple harmonic motion. To define simple harmonic motion. Recall and use equations for displacement and velocity in simple harmonic motion. Draw and use graphical representation of simple harmonic motion. So we will have graphs for this. We will learn what simple harmonic motion is. In short, we use this SHM for simple harmonic motion, and describe energy changes during simple harmonic motion. So you will see what simple harmonic motion is. There is a conversion of energy from gravitational from potential energy to kinetic energy, and again kinetic energy to potential energy. Describe the effects of damping on oscillations. So friction causes the amplitude of oscillation to decrease and eventually become zero. That is due to damping. Okay, due to friction there is damping. With practical examples, give examples of forced oscillations and resonance. Now if something is made to oscillate, okay, we are causing it to oscillate, that is a forced oscillation, and once you release the force causing the oscillation, it will naturally oscillate. For example, if you consider a swing, the swing doesn't oscillate by itself until we give it a forced oscillation. Okay, let's say there's a child on the swing, you pull the swing backwards and then you run with the swing and cause it to oscillate. After you release it, it will naturally oscillate. Okay, but in the case of the swing, if your forced oscillation is equal to the natural oscillation of the swing will oscillate with maximum amplitude. That is, then we get what we call resonance. Okay, and describe the effects of damping on resonance. Okay, so we will see these details. Okay, so what you have to remember is when the frequency of the forced oscillation is equal to the frequency of the natural oscillation of the object, then you will get resonance. Resonance occurs when the body or object vibrates with maximum amplitude. Okay, so in other words, let's say you want to make the swing with maximum amplitude. Okay, what you have to do is you have to match the natural frequency of the swing. So what that means is, if the swing is moving backwards, you have to move backwards with it. With your hands on either side of the swing, you have to move with the same rate, and when it is moving forward also, you have to move with the same rate. Then only you will be able to swing the swing with so that the swing gets the maximum amplitude of the swing. If the two frequencies or rates don't match, then you can't make the swing go with maximum amplitude. So we will see the details afterwards of different examples. Okay, so first thing is you have to know what simple harmonic motion is, but before that we will see some examples of free and forced oscillations. Okay, so here we have free and forced oscillations. So what is an oscillation? Now again, you can see this word is in green bold letters, which means you have to know the meaning of this word. I have mentioned earlier, whatever is in green bold letters in this book is extremely important. You have to know the meanings of those words, because in paper 4 they can ask you to write down the meanings of those words. Define oscillation, for example. Okay, an object oscillates when it moves back and forth repeatedly on either side of some equilibrium position. Okay, so if something, there's equilibrium or rest position, and if it moves like that, backwards forwards, that is an oscillation. Okay, if we stop the object from oscillating, it returns to its equilibrium position. For example, even in the case of a swing, the swing moves like this, right, backwards forwards, and eventually it will come to a vertical position, which is the equilibrium or rest position. Now again, I have said that the meanings of these words are in the glossary of the book. So we can go to the glossary and we can check the meaning of the word oscillation. So you can see the meaning there as well as in the glossary, so that you have a better understanding of what it means. Like I said, you should be able to write it clearly in paper 2 if they ask you. Okay, so let's go to the word oscillation. LMNO. Oscillation, a repetitive back and forth or up and down motion. We also had another word that was added to this, that which was equilibrium position. Okay, so you can use this meaning as well as the meaning that they had given you in that chapter, and add it to that. So add both together, then you will have a more complete definition. Okay, when it moves backwards and forwards repeatedly on either side of some equilibrium position. Okay, so one example is here. Okay, you can see this example over here. But once she so in the beginning, when the way she's holding the ruler, she's holding it only from here. She's pressing the ruler against the table, so the ruler will be horizontal. That will be the equilibrium position. If the ruler is not moving, the ruler will be in a horizontal position, which we call the equilibrium position. Now, if we pull this downwards, what will happen? Then this will move upwards and up and down. It will move up and down, so it will undergo what we call an oscillation. Okay, so the middle of this oscillation over here, that is the equilibrium position. So if the ruler was horizontal, it will be in the middle of this oscillation. So it will move an equal distance up and it will move an equal distance down. Okay, so horizontally it will be horizontal, that is the equilibrium, also called the rest position. So it will move up a certain distance from the equilibrium position, and it will also move down the same distance from the equilibrium position, which is what we call the amplitude. Okay, so the maximum distance that it moves up from the equilibrium position and the maximum distance that it moves down from the equilibrium position will be the same, and that is what we call the amplitude. The amplitude, you have learned previously, is the maximum displacement. Okay, when you learn about waves in the O-level classes, also you have learned what is amplitude. And by the way, we have something called natural frequency. Okay, I already explained that. Now once she pulls this down and releases it, it will naturally oscillate up and down at a certain frequency. That is what we call the natural frequency. Again, you can see this word is in green bold letters, which means you have to know the meaning of this word, and you should be able to write it if they ask you to write it, and they ask you to write the meaning in paper 4. Okay, so this is called a natural frequency of vibration. See, the easiest oscillation to understand are free oscillations. If you pluck a guitar string, it continues to vibrate for some time after you have released it. It vibrates at a particular frequency, the number of vibrations per unit time. Now frequency, you know the definition is number of waves per second or number of vibrations per second, we can say. Okay, number of oscillations per second, number of cycles per second. Okay, so that is frequency. Now yeah, so it vibrates at a particular frequency, so that is the natural frequency, and it gives rise to the particular note that you hear. Change the length of the string and you change the frequency. Now this is for the example of a guitar string. In a similar way, the prongs of a tuning fork have a natural frequency of vibration. Now you have seen the tuning forks in our physics lab. Okay, so if you pluck one of those prongs of the tuning fork, it will begin to vibrate, okay, which you can observe when you strike it on a cork. Yeah, so what we do is we strike the prongs of the tuning fork on a cork. We can't just pluck it because it's very thick, and you won't really get a vibration if you like pluck the string, but we can hit it on a cork if you pluck the prongs. Okay, every oscillator has a natural frequency of vibration, the frequency with which it vibrates freely after an initial disturbance. Okay, so here you have the meaning of the word natural frequency. Natural frequency, that is the frequency with which the object vibrates freely after an initial disturbance. Okay, we'll go back to the glossary again and have a look at this word natural frequency. Okay, everything here is in alphabetical order. FGHIJKLM, natural frequency, the unforced frequency of oscillation of a freely oscillating object. Okay, so now you know what that is. We learned what oscillation is, we learned what free oscillation is. Now forced oscillation is when something is vibrating, you cause it to you go with the vibration and cause it to vibrate. So that is a forced oscillation. Now there are some examples, we will see those, and here they have asked some questions about oscillation. Okay, we'll go through the rest of this. On the other hand, many objects can be forced to vibrate. If you sit on a bus, you may notice that the vibrations from the engine are transmitted to your body, causing you to vibrate with the same frequency. These are not free vibrations of your body, they are forced vibrations. So you're on the bus moves up and down, and that causes you to also move up and down. So you are caused to vibrate due to that force from the bus. So it is a forced oscillation. Their frequency is not the natural frequency of vibration of your body, but the forcing frequency of the bus. In the same way, you can force a meat roll to oscillate by waving it up and down. However, its natural frequency of vibration will be much greater than this, as you will discover if you hold one end down on the bench and twang the other end. Okay, so let's look at the next page. Many oscillations are too rapid or too small for us to observe. Okay, so the frequency that our eyes can detect is about 5 Hertz. More than that it can't detect. It can detect up to 5 Hertz. Our eyes cannot respond rapidly enough if the frequency of oscillation is more than about 5 Hertz or 5 oscillations per second. Anything faster than this appears as a blur. In order to see the general characteristics of the oscillating systems, we need to find suitable systems that oscillate slowly. Box 19.1 describes 3 suitable situations to investigate. Okay, so here are some examples. Spring mass system. You can see this in the diagram over here. This trolley is tethered between springs. Here is one spring, here is another spring, and will oscillate freely from side to side. So let's say you pull one end and release it, and what will happen? It will move back and forth like this. Okay, so this is the equilibrium position. Eventually, due to friction, the amplitude of oscillation will decrease, and finally it will come to rest at this position. So that's why we call this position the rest or equilibrium position. So you can pull it to either end. Let's say we pull it this way and we release. Then what will happen? It will go like this, like this, like this, and eventually due to friction there is damping. Okay, so damping means the amplitude becomes lesser and lesser, and eventually it will become 0. Okay, so a trolley loaded with extra masses is tethered by identical springs in between 2 clamps. You can see here there is one G clamp, and over here there is another G clamp. Now when you all were doing practicals for paper 3, you used these apparatus, and here we have a stand. Okay, so here is the rod of that stand. This is the vertical part. Those are the rods of the stands, and through the rod they have put the spring. You can see the spring over here. So one end of the spring, that circular part of the spring, has been put through this this rod has been put through the circular part of the spring. And here we have the trolley. Displace the trolley to one side and it will oscillate back and forth along the bench. Listen to the sound of the trolley moving. Where is it moving fastest? What happens to its speed as it reaches the ends of the oscillation? What is happening to the springs as the trolley oscillates? Now what happens is you pull it to the one side, either to the left or to the right, release it, and once you release it, what will happen? It will accelerate until it comes to the equilibrium position, and then what happens? It begins to decelerate, and eventually it comes to a momentary stop at the other end. So at each end the trolley will come to a momentary stop. Okay, so once it's leaving any end, it will start to accelerate until it comes to the equilibrium position, okay, which is the middle here. So the trolley, once you release, it will go like this, because now when it is on this side and if you release it, this spring is compressed, this spring is extended. So what will happen is this spring will try to get uncompressed, so there is a force on the trolley to the left by this spring, because it is compressed, so it tries to get uncompressed. Therefore there is a, when the trolley is pulled to this side, there is a force on the spring to the left, and there, this spring over here is pulling the trolley to the left because this spring is stretched, so it will pull this way. Okay, so what will happen is this spring will exert a force to the left, this spring will exert a force also to the left when it is over here. Therefore there is a net force on the trolley to the left. But what happens is when it comes to the equilibrium position, both springs are pulling by the same amount of force, so there is no net force on the spring when the trolley is in the middle. But when the trolley moves to the left, what will happen? Now the force is the other way, because when the trolley is on this side, this spring is extended and this spring is compressed. So this spring will pull the trolley to the right, this spring will push the trolley to the right when the trolley is on this side. Okay, that is when the trolley is to the left of the equilibrium position. So there will be a net force to the right. Now what happens is, you have learned previously that if the resultant force is opposite to the direction of motion, the object will decelerate. If the resultant force is in the direction of motion, the object will accelerate. Now that is what happens. Now in the beginning, when we pulled this to this side, the trolley to this side, both forces are to the left, and the trolley also begins to move to the left until it comes to the equilibrium position. So if the resultant force and the direction of motion are the same, the trolley will accelerate. That's why the trolley accelerates or speeds up. In other words, acceleration means there is increase in speed. So the reason the trolley accelerates until it comes to the equilibrium position is because the resultant force on the trolley is in the direction of motion, which is to the left. But after this point, what happens is the trolley decelerates because the resultant force is to the right, which is opposite to the direction it is moving. So as soon as it passes the equilibrium position, still it is moving to the left until it comes to a momentary stop at the other end. Now when during that part of motion, the resultant force is to the right, the motion is to the left, the two are in opposite directions, so the trolley decelerates. It comes to a momentary stop here. Okay, so from the equilibrium position, when it is moving to the left until it comes to the maximum position or until it comes to a momentary stop, it will decelerate. And afterwards what happens? Again it will start accelerating until the equilibrium position here, and this process continues. Okay, so here we have a simple harmonic motion. It is moving back and forth about this equilibrium position. Something similar we have here also in the case of the pendulum. Once you release the pendulum, okay, the equilibrium position of the pendulum is when the pendulum is vertical. Okay, it's like the example of the swing that I mentioned earlier. Okay, so when the pendulum is vertical, the pendulum is in the equilibrium position. Equilibrium position is when the oscillation stops and the pendulum comes to a stop. Same thing here, when the oscillation stops and when it comes to a stop, that position is the equilibrium position. Okay, so once you release this, what will happen? In the beginning, the initial speed is 0. Okay, then you release. Then what happens? The speed keeps on increasing until it comes to the equilibrium position. And then what happens is, once it passes the vertical position or equilibrium position, it will begin to decelerate. It decelerates until it stops on this side. And then again, it starts to accelerate up to the equilibrium position. Then again, it decelerates from the equilibrium position to the next position where it comes to rest. And this process continues. Okay. So here is another example. A long pendulum at least 2 meters long hangs from the ceiling with a large mass fixed at the end. Okay. Figure 19.4. A long pendulum oscillates back and forth. Pull the mass some distance to one side and let go. The pendulum will swing back and forth at its natural frequency of oscillation. Why natural frequency? Because once you release it, it oscillates by itself. It swings by itself. So it is swinging due to its natural frequency. It's swinging with its natural frequency. Frequency is the number of swings per second in this example. Here we can also say number of oscillations per second. Try to note the characteristics of its motion. In what ways is it similar to the motion of the oscillating trolley? In what ways is it different? Okay, here it is moving in a curved path. Here it is moving in a straight line. So that is one difference, but everything else is the same. Up to the equilibrium position, it will accelerate, and then once it leaves the equilibrium position until it comes to a momentary stop, it will decelerate, and this process continues. Okay, so the resultant force, you will notice, is always towards the equilibrium position. If this trolley is on the right side, the resultant force is to the left, which is towards the equilibrium position. Now in this position, the resultant force is 0, and the equilibrium position, the resultant force is 0. And again, if you move, if this is on the left side, the resultant force is to the right. There is a compression on this spring when it is on this side, so that spring exerts a force to the right, and when the trolley is on this side, this spring is extended, so it will pull the trolley to the right side. So both forces from the spring will be to the right when the trolley is on the left, and when the trolley is on the right, both forces from the spring is to the left. So you will see that both the resultant force is always directed towards the equilibrium position by the springs. Example number 3. I think we answered all these questions, right? Okay, by the way, where is the trolley moving the fastest? It will be moving fastest at the equilibrium position. Okay, because once it is here, the speed is 0, so the speed keeps on increasing until it reaches the equilibrium position. As soon as it passes the equilibrium position, it will start to decelerate. Okay, so over here the speed is 0 at one end, then when you release it, its speed keeps on increasing up to this point, and afterwards what happens, it starts decelerating after it passes the equilibrium position. Again, over here speed is 0 at the maximum position, over here at this end, then again it comes back this way, so the speed increases, and then becomes the maximum value. Then after it passes the equilibrium, speed will decrease. So it will be moving fastest at the equilibrium position. What happens to its speed as it reaches the ends of its oscillation? It slows down. So once it passes the equilibrium position, and when it comes to the other end, after passing the equilibrium position, and when it comes to the other end, what will happen? It will decelerate. But from the position where it is at rest, when it comes to the equilibrium position, it accelerates. So again, over here, when it is here, it is at rest, and when it comes back this way, the speed will increase. So when it is coming from its the position where it is at a momentary stop to the equilibrium position, the speed will increase. But when it is going from the equilibrium position to the position where it comes to a momentary stop, it will decelerate. What is happening to the springs as the trolley oscillates? The springs get compressed and extended. Okay, so I think yeah, we answered all these questions. Okay, here is another example, a loudspeaker cone. Now this loudspeaker cone can be set to vibrate at the frequency that we want it to vibrate using the signal generator. Okay, we set the frequency that we want this to vibrate or produce sound using this signal generator. We can give it a fixed frequency so that the frequency doesn't change. So if we set the frequency, for example, at 50 Hertz, this will keep on vibrating at 50 Hertz. It will not fluctuate. Let's say it will not become 40, 50, 80, 100. It won't fluctuate. So if we set this at 50 Hertz, this will begin to vibrate at 50 Hertz. This will vibrate at 50 Hertz. That means it will move back and forth with a frequency of 50 Hertz per second, 50 cycles per second, or 50 vibrations per second. And you know, the frequency of the source is the same as the frequency of the waves it produces. So the frequency of the sound waves that this cone produces, that the speaker cone produces, will also be 50 Hertz. The frequency of the source is the same as the frequency of the waves it produces. A signal generator set to low frequency, say 1 Hertz, drives a loudspeaker so that it vibrates. Okay, so if it's 1 Hertz, it will vibrate at a frequency of 1 cycle per second, because frequency means number of cycles per second or number of vibrations per second. We can also say number of oscillations per second. So it will vibrate up and down like this at a rate of 1 vibration per second if the frequency of vibration is 1 Hertz. Okay, so what is happening is, this is the signal generator that will make this thing vibrate up and down. Okay, so here it's a forced oscillation because this is the one causing it to oscillate up and down, this signal generator. Okay, but over here what we saw, and what we saw over here were what? Were free oscillations, because they were vibrating by themselves. After you release them, they vibrate by themselves, so that was a free oscillation. But over here we get a forced oscillation. And previously you saw the example of the bus. When you are going on the bus, we vibrate up and down, we move up and down because the bus is making us do that. So when the bus goes over a pothole or goes over a bump, the bus moves up, and then we also move up. So the bus is making us move up, so that is a forced oscillation. Now similarly over here also, the signal generator is causing this to vibrate up and down at the frequency that we set the signal generator to. So therefore again here we have a forced oscillation. Okay, you need to be able to see the cone of the loudspeaker. How does this motion compare with that of the pendulum and the spring mass system? Okay, over here also what will happen is the cone will move up and down. You would have seen the speaker cone. Now if you look at a speaker, you can't see the cone which is inside because of that mesh like thing in the front. But if you open that part, okay, of the speaker, you will see there is something like this inside that, and when it is switched on, you will see that this is moving forwards backwards, like this, up and down. Okay, when you if you open the speaker, you can see it. You switch it on and then you will see this moving up and down or forwards backwards. Okay, so something like this. Okay, here also it's moving backwards forwards. Okay, so how does it compare with the pendulum and the spring mass system? Again, we have simple harmonic motion. Now we will I think it's easier if we go through the definition of simple harmonic motion, because you will have that again and again, and you have to study or memorize the definition of simple harmonic motion, because you will have to write that in paper 4. Almost always they ask you the definition of simple harmonic motion, and it is given in your book. Okay, so here they have given the requirements for something to have simple harmonic motion, SHM, and I think they have given the definition also previously. Anyway, we will come to that and we can go through it in detail after that. Okay, so it's not alright, so what we'll do is we'll come back to it. Anyway, it's better to show you the definition now. Okay, here it's here. Simple harmonic motion is defined as follows: a body executes simple harmonic motion if its acceleration is directly proportional to its displacement from the equilibrium position and in the opposite direction to its displacement. Now you can see we have learned that always the resultant force and acceleration are in the same direction. That is under Newton's second law. We learned it. Even in the small O-level classes you have learned it. So what will happen is, when this is, for example, if this trolley is to the right of the equilibrium position, the resultant force is to the left, and resultant force and acceleration are always in the same direction. So the acceleration is to the left, and when this trolley is on the right side, left side, the resultant force due to the springs is to the right of the trolley. So then the acceleration is also to the right. Okay, so that's what this means over here. A body executes simple harmonic motion if its acceleration is directly proportional to the displacement from the equilibrium position. Now one more thing is, when it is at this position, the resultant force is 0. But if you move it more and more to the left, the force also becomes more and more, because one spring is getting compressed more and more, and the other spring is getting extended more and more. So the more you compress a spring, or the more you extend a spring, the more will be the force from the spring. You know, F is equal to kx. K is the spring constant, X is the extension or compression. So the greater the X, the greater will be the force in the spring, or force from the spring. So the more you move it to the left, or the more you move it to the right, the greater will be the compression on one spring, and also the greater will be the extension on one spring. So therefore the force exerted will be more and more the more you move to the left or to the right of the equilibrium position. Okay, so when the resultant force increases, the acceleration also increases. Okay, so that's what you can see over here. A body executes simple harmonic motion if its acceleration is directly proportional to its displacement from the equilibrium position. Now the more you move away from the equilibrium position, the greater will be the resultant force, and then the greater will be the acceleration. And over here the resultant force is 0. So when it is at the equilibrium position, the resultant force is 0, so the acceleration is 0. You know, from F equals ma, if the acceleration is, if the resultant force is 0, acceleration is 0. So at this position there is no resultant force. There is a force. Maybe this spring is pulled, so this spring also pulled, extended. So there can be a force on either side, but it cancels out. Okay, so at the equilibrium position there is no resultant force, and no resultant force means no acceleration. No acceleration at the equilibrium position. Okay, so you can see, but the more and more you move to the left or to the right of the equilibrium position, the greater will be the resultant force, and therefore the greater will be the acceleration. A body executes simple harmonic motion if its acceleration is directly proportional to its displacement from its equilibrium position. Okay, I think the first part is clear. And in the opposite direction to its displacement. Okay, I told you the more and more it moves to the right, the greater and greater will be the resultant force, but it is to the left. Now the more and more it moves to the left, or whenever it is on the left side, the resultant force is to the right. Whenever this trolley is on the right side of the equilibrium position, the resultant force is to the left. So that's what they mean by this last part of the sentence, and in the opposite direction to its displacement. Okay, so you have to write this whole thing in order to get the full marks for the definition. If you miss even one thing, like if you miss the word, let's say opposite and directly proportional, then you wouldn't get the marks. So that's why we ask you to memorize the definitions with understanding, and whatever is in the green boxes in this book is extremely important. You have to memorize it with understanding. Okay, then we'll continue. Okay, here we were talking about this. Okay, so how does this motion compare with that of the pendulum and the spring mass system? So very simple. Here also it's a up and down or simple harmonic motion. Try using a higher frequency, say 100 Hertz. Now previously we used 1 Hertz because our eyes can detect up to 5 Hertz. Okay, we learned that earlier. So if it is 1 Hertz, then our eye can see the motion. But if it is greater than 5 Hertz, about 5 Hertz, greater than about 5 Hertz, then your eyes will not be able to detect the oscillation. Try using a higher frequency, say 100 Hertz. Use an electronic stroboscope flashing at a similar frequency to show up the movement of the cone. It may help to paint a white spot on the center of the cone. Do you observe the same pattern of movement? Okay, you have to know what this stroboscope is. I think in the AS class also I explained this. Now there are different stroboscopes. Okay, the most common one that we use in the A-level classes is the stroboscope that gives flashes of light. So we can adjust the rate at which it gives out the flashes of light by using the settings in this. So what happens is this cone is vibrating at a frequency that our eyes cannot detect. But if this stroboscope gives out flashes of light as the same frequency as the frequency of vibration of the stroboscope, you will notice that the if the stroboscope gives the same frequency of vibration as the cone, if it gives light at the same frequency of vibration of the cone, you will see that the cone appears stationary. So the cone is vibrating up and down, but this gives out the flash of light at the frequency of vibration of the cone. So when it flashes onto this, you will see that the cone appears stationary. Why is because, let's say the cone goes down, goes up, and then that is one cycle. So let's say we start at the topmost position of the cone, it goes down all the way to the bottom and then comes back up. That is one oscillation. So let's say at this moment the light flashes. As soon as it comes to the topmost position, the stroboscope gives a flash of light. Okay, and then it goes down again and then comes back up again. And then at that moment again, the stroboscope gives a flash of light. Again it goes down and then comes back. Again, at the moment it comes to the highest position, the stroboscope gives a flash of light. Now you can see the frequency that the stroboscope gives the flashes of light is the same as the frequency of oscillation of the cone. Now when this happens, because the flash of light is happening every cycle of the cone, you will see that the cone appears stationary to our eyes. Okay, so when it appears stationary, we know that the stroboscope is giving light at the same frequency as the vibration of the cone. Okay, so to it may help to paint a white spot on the center of the cone. Do you observe the same pattern of movement? Okay, stroboscope can be used to find the frequency of oscillation of an object. Now even this frequency, once you set the signal generator to that particular frequency, it will vibrate at that frequency. So the stroboscope should also give you, once it is set so that this appears stationary, it should give you the same frequency as the settings on the signal generator. Again, if you are not familiar with the stroboscope, there is a video, you can search it about using the stroboscope. Okay, when you go online, you can search it. You will see there are several videos online where they show you how to use this stroboscope, how to set the settings. There is an example. Okay, best thing you can use this is for a fan. Okay, so if the frequency of the flashes of light of the stroboscope is the same as the frequency of rotation of the fan, you will see that when the fan is if the fan is rotating at a frequency higher than 5 Hz, we can't see the fan rotating. It will appear as if there is no fan there, no fan wings. Okay, but if you use the stroboscope and if you set it to the setting so that it is the same frequency as the fan, you will see that the fan appears stationary, because after every turn there is a flash of light. After every turn there is a flash of light. So you will be able to see the wings of the fan when the stroboscope frequency is the same as the frequency of the rotation of the fan. To help you understand this better, like I said, there are videos you can search online. You will see videos where how the stroboscope is used. Alright, so here are some questions. State which of the following are free oscillations and which are forced oscillations. Okay, wing beat of a mosquito. The wing of a mosquito is made to beat by the muscles of that mosquito contracting and relaxing. So the wing is made to oscillate. Therefore, it is a forced oscillation. Okay, then movement of the pendulum in a grandfather clock. That is a free oscillation. Now, in the grandfather clock, you release the pendulum, it continues to vibrate just like this. So it's a free oscillation. Then over here, the vibrations of a cymbal after it has been struck. So you strike it once, then those cymbals are vibrating by themselves. So again, it is a free oscillation. So here forced, free, free. The shaking of a building during an earthquake. Now we are talking about the building. The building is made to vibrate by the earth vibrating. Okay, so the building is forced to vibrate due to the vibration of the earth. Therefore, this is a forced oscillation. Okay, so here forced, free, free, forced. Okay, let's check the answers. See, forced, free, free, forced. Alright, so that's the end of that page. We'll go to the next page now. Okay, 288. Describing oscillations. Now in the O-level classes also you have learned the meanings of these words. Again, even in the A-level classes you have to know the meanings of these words, okay? And even in the AS class you have learned this, so in A2 also you should know. Again, in paper 4 they can ask you, state what is amplitude, frequency, period, wavelength, okay, displacement. So you should know the meanings of all. What is phase, out of phase difference, coherent sources, destructive interference, constructive interference, very important. You have to know the meanings of all, and also in the glossary of your book the meanings are given, and also throughout the chapter in those green boxes the meanings are given. Previously we learned about simple harmonic motion, and I told you what happens at each position, that is at the extreme ends where it comes to a momentary stop, in the middle of the oscillation which is at the equilibrium position it has the maximum speed, and I also told you when it goes from the equilibrium position to the extreme position it decelerates, and when it comes from the extreme position towards the equilibrium position the object accelerates. So they have summarized it over here. I will go through this sentence. Everything in this paragraph is extremely important. You have to understand this very clearly. All of these examples show the same pattern of movement. The trolley accelerates as it moves towards the center of the oscillation. So when it moves from the extreme end towards the center, the trolley speed increases. Speed increasing means it accelerates. It is moving fastest at the center. So at the equilibrium position, the speed is maximum. It decelerates as it moves towards the end of the oscillation. So as soon as, from the equilibrium position to the extreme end, when it is moving from the equilibrium position towards the extreme end, that is where it comes to a momentary stop, it decelerates. So from the equilibrium position to the position where it comes to a momentary stop, it will decelerate. So that's what the next sentence here means. It decelerates as it moves towards the end of the oscillation. At the extreme position, it stops momentarily, reverses its direction, and accelerates back towards the center again. So that is what happens here. So once it goes to the extreme end, it reverses the direction and it comes back towards the equilibrium position. Okay, again at the extreme position it stops momentarily, reverses its direction and accelerates back towards the center again. Always the acceleration is towards the center. No matter wherever the object is that is undergoing simple harmonic motion, the acceleration is always directed towards the equilibrium position or towards the center. Okay, then I talked about this earlier. There is a graph that we can draw for this kind of motion. Here we have the displacement time graph, but you will also see velocity time graphs and acceleration time graphs later on in this chapter. Okay, so here we have the displacement time graph, so make sure you have a good understanding of this. The displacement x varies in a smooth way on either side of the midpoint. Okay, remember displacement is a vector quantity, so we start considering the displacement from the equilibrium position. Okay, so maybe if we can take to the right as positive displacement, then whatever is to the left will be a negative displacement. The displacement x varies within a smooth way on either side of the midpoint. So midpoint is the center or the equilibrium position. The shape of this graph is a sine curve and the motion is described as sinusoidal. Why sinusoidal? Because the shape is a sine curve. So if it's the shape of a sine or cosine curve, we say it is sinusoidal. A displacement time graph to show the meaning of amplitude and period. Alright, we'll apply this graph for the trolley. Now let's say we start from the right side. If we start from the right side, let's say we pull this to the right side and we release it. So it goes like this, goes like that, goes like this, goes like that. Okay, so we will start the timing as soon as it passes the equilibrium position and is moving to the right. Okay, so in the beginning we released it from here, goes like this, goes like this, and then we start timing as soon as it passes the equilibrium position and is moving to the right. Okay, so at this position and it's moving to the right. Okay, so in the beginning, as soon as we start at the time, the displacement is 0 because it's at the equilibrium position. Then what happens? It's moving to the right and we take to the right as positive. Normally, if something is moving to the right or moving upwards, in the positive x-axis direction or in the positive y-axis direction, which is to the right and upwards respectively, then we consider that as positive. So since this is moving to the right, which is towards the positive x-axis direction, we can take the displacement to the right as positive, which is the standard way. Okay, you can even take to the left as positive, but normally we take to the right as positive. Okay, so we take to the right as positive, and what happens is to the right the displacement is increasing. Then over here the displacement is maximum. Now this is where the trolley comes to a momentary stop. It is the extreme position. Okay, so over here, this point here is the extreme position. That is the position where the trolley comes to a momentary stop, and then it starts changing its direction. It starts moving back to the left, Okay, so over here it comes to a momentary stop, and then what happens? It starts moving to the left. Now it's moving to the left, and then it comes back to the equilibrium position. Now to the right of the equilibrium position, the displacement is positive. To the left of the equilibrium position, the displacement is negative. So what happens is, in the beginning it moves to the right, and then it comes to the extreme position, then it moves back to the left. But when it is moving back to the left, you can see that the positive displacement is decreasing, and when it comes back over here, the positive displacement becomes 0. So from here to here, this part of the graph is when the trolley is on the right side and is moving to the left. Okay, so it's on the right side, but it's moving to the left, and it comes to a momentary stop. So that is what is shown by this portion of the graph. Then what happens? So after this position, when it is here, the trolley moves to the left and comes to a momentary stop over here. So the trolley moves like this to the left, and then comes to a momentary stop on this side. Now to the left we have considered the displacement is negative. So what happens? It's moving more and more to the left, and it becomes comes to the extreme position. So the displacement becomes more and more negative, and it reaches its maximum value over here. So the displacement becomes more and more negative, and it comes to a momentary stop there. Then after that, what happens is it comes back to the right. Okay, so it comes moves to the right. Now, but even if it moves to the right, we took to the left of the equilibrium position as negative displacement. So what happens? It moves like this, and it comes to a stop. So what happens is the negative value of displacement decreases when it is on the left side of the equilibrium position and is moving to the right side. I hope it's clear. Okay. Alright, so what happens over here? Now this, you can see over here it reaches the maximum displacement at this position, maximum negative displacement. Then what happens? Now this is the portion of the graph where the trolley is moving to the right. The trolley moves to the right, but it is still on the left side of the equilibrium position. So what happens? The negative displacement keeps on decreasing and becomes 0. And this is at the equilibrium position again, where the displacement is 0. Then the process continues. Now you can see again, one more thing is, this is a displacement time graph, and you have learned that the gradient of a displacement time graph is the velocity. Okay, so you can see at the extreme positions where the displacement is maximum, the gradient is 0. So if you draw a tangent at this point, you will see the line will be horizontal. Same thing here, the line will be horizontal. At the equilibrium positions, the displacement is maximum, but the velocity is 0. The way you find the velocity of a displacement time graph is from the gradient. So if you want to find the gradient, you can draw a tangent over here. You will see that the tangent is a horizontal line. If it's a horizontal line, the gradient is 0. Okay, so the gradient is 0 here and 0 here. That means at the extreme positions, the velocity is 0. Now you can see that the gradient of the tangent or gradient of this curve will be maximum over here and over here, which is at the equilibrium positions. Okay, I already explained this before. At the equilibrium position, the velocity is maximum. So if you draw the tangent over here or here, which is at the equilibrium positions, the velocity is maximum. But you can see here the velocity is negative, over here the velocity is positive. Here the velocity is negative. Now this is when it comes back this way. So it moves like this and it comes back this way. Can you see it's moving to the left? So this point over here is when it is moving to the left, and it is at the equilibrium. It's moving to the left. So I told you, if it is moving to the left, anything to the left is negative, anything to the right is positive. So over here we start at the timing when the trolley is moving this way. So it goes like this and comes back. Now this is where the velocity is negative over here. Now here you can see the velocity is maximum and positive. That is when we start at the timing, which was when it was moving to the right. Okay, from here moving to the right. Okay, so then what happens again over here? So the trolley goes like this. Then we saw that over here it's moving to the left, the velocity is negative. Then it goes like this and comes back this way. Now it is moving to the right now, and it's at the equilibrium position. So moving to the right means velocity is to the right. So it should be positive, because by standard to the right is positive. So you can see here, over here, if you draw the tangent, you can see the gradient of the tangent is maximum and positive over here, which is at the equilibrium position. Okay, it's very important that you understand this, okay, because you will be tested on it again and again. Make sure it's very clear. Okay, and all these labels are important. You can see here the maximum displacement is the amplitude, which is at the extreme positions at the two ends. And here we have positive amplitude, here we have from here to here negative amplitude, and this is the time axis. So from one point on the wave to the next adjacent point, that is one period. Now if this was distance, then it will be wavelength. Okay, but here we can't have a distance one, we have to have time. Okay, so therefore this is the period. So for example, from here to here, what happens is, let's say it's at this end, it goes like this and completes one cycle. It comes back to this position. That is one whole cycle. So one whole cycle means from here to here. That is the period. Okay, so notice that the displacement changes between positive and negative values as the object moves through the equilibrium position. Now I already explained that why it changes from positive to negative, because to the right of the equilibrium position is positive, to the left it is negative. The maximum displacement from the equilibrium position is called the amplitude, x naught. Again, you can see this word is in green bold letters. Even you had it in the AS class, so you should know the meanings of these words: amplitude, frequency, wavelength. I also told it earlier. Okay, x naught of the oscillation. The displacement time graph can also be used to show the period and frequency of the oscillation. The period t is the time for one complete oscillation. Note that the oscillating object must go from one side to the other side and back again, or the equivalent. So that's what I explained. So if we start at this point, it has to go like this and come back to the same point. That will make one complete oscillation or one complete cycle. But again, the frequency f is the number of oscillations per unit time. Okay, frequency is the number of waves per second, number of cycles per second, number of oscillations per second. So per second means per unit time. Okay, and so f is the reciprocal of t. You know, you have learned this equation already. Frequency is 1 over the period, or period is 1 over the frequency. So once you know the period, you can find the frequency, or if you know the frequency, you can find the period. All right, so here is another question. Let's do this question. I'll go through some questions because this is a topic that you really need to understand, and I have noticed certain students having difficulty in this topic, especially when they learn it in school. From the displacement time graph shown in figure 19.8, determine the amplitude, period and frequency of the oscillations represented. So we need to find amplitude, period and frequency. Okay, so very easy. You can find the amplitude, that is the maximum displacement. The period is the time for one complete cycle. So you can see if you start here, you have to go all the way to the next adjacent point on the wave. That is one cycle. So 120 milliseconds is the period. Then frequency we can find 1 over the period using this formula. 1 over 120 milliseconds will give you the frequency. Okay, let's do it quickly. Now I will zoom in because it's difficult to see this. So the maximum displacement is the amplitude, that is the height of the crest or the depth of the trough. So from here to here, from the this is the equilibrium position, the height of the crest or the depth of the trough. So its amplitude is 10 centimeters. Okay, let's look at the answer. 10 centimeters. And I told you period is the time for one complete cycle, that is 120 milliseconds. We saw that earlier. Then frequency is 1 over the period. Now here they have converted it to seconds, so 0.12 seconds. So the frequency is 8.3 hertz. Okay, so one whole cycle, 120 milliseconds. By the way, we missed this question, so let's go through the second question. We did the third one. If you could draw a velocity time graph for any of the oscillators described in box 19.1. Box 19.1 is this one. What would it look like? Would it be a curve like the one shown in figure 19.6a, or triangular, saw-toothed? See, saw-toothed, like the one shown in figure 19.6b. Two possible velocity time graphs for vibrating objects. So you know it has to be curved like this, and we saw it over here also, because there is no here it indicates that there is a sudden change in the velocity. There is, and here also you can see if it's a straight line, that means the velocity is constant. The velocity isn't constant, because the acceleration here, not velocity here, if you get this kind of graph, that means the gradient of the velocity. This was a displacement time graph. Okay, so here this is a velocity time graph, and yeah, so very important thing is, first thing, you look at the axis. Whenever you get a graph, make sure you have a good look at what the axes are, because sometimes you might confuse. Now in the beginning when you see it like this, you might think, oh, it's a displacement time graph, but no, it's a velocity time graph. So when it's a velocity time graph, it's different. So here what happens is the velocity is changing with time, and the gradient of a velocity time graph is acceleration. Okay, so here if you look at this graph, the acceleration is constant, but over here the gradient is not constant, it's changing, it becomes 0. And then again what happens, the acceleration becomes negative and decreases and becomes 0. Again it increases, positive maximum, and then decreases and becomes 0. So over here you can see the acceleration is changing. Okay, but here you can see acceleration constant. But the acceleration, you know, depends on the force, and the force keeps on changing depending on how much the spring is compressed. For example, over here the spring gets more and more compressed, and the other spring gets more and more extended. Okay, so when the springs are getting more and more compressed and more and more extended, the force exerted by the spring also gets more and more or less and less. Okay, depending on where the position of them. So when the force is changing, since the mass is constant, the acceleration also changes gradually. So the acceleration changes gradually and becomes 0. Okay, so over here, you know, the acceleration is 0 at the equilibrium position. The resultant force is 0, so the acceleration is 0. Okay, so it is a gradual process. It doesn't suddenly change. Now over here it's indicating that the acceleration, it doesn't even show that the acceleration is 0, but over here the acceleration becomes 0, and then the direction of acceleration changes. So here at one time the acceleration is to the right, and the other time the acceleration is to the left, but it's always directed towards the equilibrium position. Okay, so it can't be a sudden change like this, so it has to, the answer is curved, figure 19.6a. Okay, curved. Alright, so that's the end of those topics. Now we come to the next topic, which is phase. Again, you can see this is in green bold letters. Phase difference also is in green bold letters, which means you should know the meaning, because in paper 4, like I said, they can ask you the meaning. The term phase describes the point that an oscillating mass has reached within the complete cycle of an oscillation. So very simple. The term phase describes the point that an oscillating mass has reached within the complete cycle of an oscillation. Okay, so that is the point that the oscillating mass has reached within the complete cycle of an oscillation. It is often important to describe the phase difference between two oscillations. Okay, so previously we learned about path difference and phase difference. Okay, so you know the difference. Now if it's a path difference, we give it in terms of wavelength. If it's a phase difference, we give it in terms of angle. The graph of figure 19.9a, that is on the next page, shows two oscillations which are identical except for their phase difference. Okay, we'll have a look at that one. 19.9a, here B, C. Okay, figure 9 shows two oscillations which are identical except for their phase difference. They are out of step with one another. In this example, they have a phase difference of 1/4 of an oscillation. So remember this, they are out of step with one another, and they have a phase difference of 1/4 of an oscillation. So that means one wave should be ahead or lagging behind the other by a quarter of a wave. Okay, phase difference can be measured as a fraction of an oscillation. So I said quarter of a wave, in degrees or in radians. Now when we say phase difference, I told you we give it in terms of angle. So angle can be in degrees or in radians. Let's see this. Now you can see here, can you see it's quarter of a wave? If you look at this closely, can you see from here? Okay, let's consider this black line curve, black wave. So from here to here, that is one wavelength. Okay, so from here to here, this will be quarter of a wavelength. Okay, so again from here to here, one whole wavelength. From here to here, half a wavelength. Forget about the green one, just think only the black one is there for now. So if you look at this black wave, from here to over here, that is one whole wave. So from here to here is half a wave. From here to here is quarter of a wave. Now look, think of the green one. Now can you see the green wave starts after 1/4 of the black wave? See, the green wave, see, it starts from here. So that's why we say it is quarter of a wave behind the black wave. So we can say, now see the time here, starts at 0, but the time here is more. So the green wave is lagging behind the black wave by quarter of a period. Okay, so the phase difference in degrees is quarter of a cycle. Okay, so we have to give it in degrees. So that is by 90 degrees, because quarter of a wave is 90 degrees. Okay. So when we say phase difference, we give it in terms of angle. So one whole wave, we take it as 360 degrees. Half a wave is 180. Quarter of a wave is 90 degrees. So one wave is lagging behind the other. The green wave is lagging behind the black wave by 90 degrees, by a phase difference of 90 degrees. If we say path difference, by quarter of a wavelength. Okay, so because they are not going together, they are out of step with one another, and they have a phase difference of 1/4 of an oscillation. Phase difference can be measured. Now see, phase difference is given in terms of oscillation. Also we can give it in terms of angle, but normally we give it in terms of angle. Okay, and they ask us to go through worked example 1. Okay, and by the way, if you analyze this, here it is out of step, or we can also say out of phase, anti-phase, by 180 degrees. Okay, you can see this now. If you start with this wave, the black wave, from here to here, one complete wave, but this one, the green wave, starts here, we can say. Can you see it's after one whole cycle, after not one whole cycle, half a cycle, sorry, it's half a cycle, not one whole cycle. See, from here to here, half. So this thing, see, this thing starts after one half or half a cycle. So here it is antiphase or out of phase, or we can say the phase difference is 90 degrees, or we can also say the phase difference, like what they say here, have a phase difference of half of an oscillation for this. Okay, here it's different, so we can't really say it for this because the frequencies are different here. Here the frequencies are the same. Okay, let's go through this example. Worked example. Figure 19.10 shows displacement time graphs of two identical oscillators. Calculate the phase difference between the two oscillations. Now they say identical oscillators, that means think we have to assume that the frequency is the same. Frequency of the waves is the same. Okay, frequency is the same. Give your answer in degrees and in radians. So phase difference, that means we have to find by how much one wave is lagging behind the other, or we have to find by how much one wave is ahead of the other. Now you can see this blue wave is ahead of the green wave because the blue wave, it starts at time t equals 0, but this wave starts at time somewhere like 18 milliseconds, right, after the blue wave. See, the same point on the wave starts at about 18 milliseconds after the blue wave. Okay, you have to see it from the same point. Now you can't take it start the timing here. It has to start from the same point. Okay, we'll see. Give your answer in degrees and in radians. The displacement for two oscillators with, they say the displacement time graphs for two oscillators with the same period. Same period means the frequency is also the same, because period is 1 over frequency. So the period is the same, the frequency is also the same. Okay, so here they have mentioned steps. Measure the time interval t between two corresponding points on the graph. So what we can do is from here to here. Okay, so you see that's 17. Now by looking at this I said 18, but we have to analyze it, look at it closer so we get the exact value. Okay, so here from here to here 15, 16, 17. You see here 17. 1, 2, 3, 4, 5. Okay, then 10, 15, 16, 17. Okay, so the one wave is lagging behind the other by 17 milliseconds. Okay, now the time for one complete wave, what is the period? That is 60 milliseconds. See, you go like this, one whole wave. Again we can zoom in and have a look. Yeah, 60 milliseconds. So we have to see, here it's 17 milliseconds, here it's 60 milliseconds. So how much of a fraction is that? 17 out of 60. Okay, so 60 milliseconds, see, 17 out of 60. So that means 0.283 of an oscillation. Now this is in terms of oscillation, the phase difference is given, but I told you phase difference we usually give in terms of angle. Okay, so then it's 0.283 of an oscillation. So the phase difference is 0.283 times 360 degrees times 360 degrees, because 17 for 60 milliseconds, therefore for one whole wave that is 360 degrees. Okay, so that is 102 degrees. If you approximate it to two significant figures, that will be 100 degrees. Now this is phase difference in degrees. You can also get phase difference in radians. Now 60 milliseconds is for one whole wave. 60 milliseconds is for one whole wave. So 17 divided by 60 into 360 degrees is also for one whole wave. Then you get 100 degrees, or 17 divided by 60 into 2 pi radians, because for one whole wave it is 2 pi radians. So we get 1.8 radians. Okay, so the phase difference is 100 degrees or 1.8 radians. This is in degrees, this is in radians, this is in terms of oscillation, like what we saw over here in the previous page. We learned that okay, phase difference you can give it in terms of oscillation also. Okay, So I think this example is very clear now. Let's go through the rest of this page. Okay, so now they introduce simple harmonic motion. There are many situations where we can observe the special kind of oscillation called simple harmonic motion, and you can see again this word is in green bold letters, which means you have to know the meaning, you have to know the definition, and I also already showed you the definition. Some are more obvious than others. For example, the vibrating strings of a musical instrument show simple harmonic motion. When plucked or bowed, the strings move back and forth about the equilibrium position of the oscillation. The motion of the tethered trolleys in figure 19.3, which is what we saw earlier, figure 19.3, this one, and that of the pendulum in figure 19.4, which is this one, are also simple harmonic motion. Simple harmonic motion is defined in terms of the acceleration and displacement of an oscillator. Page 294. Already I showed it to you. Okay. So the definition was here. See. Okay. We went through this already. Here are some other less obvious situations where simple harmonic motion can be found. So here are more examples of simple harmonic motion. When a pure single note sound wave travels through air, the molecules of the air vibrate with simple harmonic motion. So single tones, particular frequency. So the air molecules move up and down or move backwards and forwards. It can be move up and down or sideways or whatever direction. It moves about a fixed position. When an alternating current flows in a wire, the electrons in the wire vibrate with simple harmonic motion. You know, you have learned for electricity, AC and DC, alternating current and direct current. So in alternating current, what happens? The electron moves backwards, forwards, like that. Okay, so there is an example of simple harmonic motion for the electron. There is a small alternating electric current in a radio or television aerial when it is tuned to a signal in the form of electrons moving with simple harmonic motion. Okay, so there is a small alternating electric current in a radio or television aerial when it is tuned to a signal in the form of electrons moving with simple harmonic motion. Okay, so you have to tune it to that signal and then the electron is moving backwards, forwards, so it's exhibiting simple harmonic motion. The atoms that make up a molecule vibrate with simple harmonic motion. See, for example, the hydrogen molecule in figure 19.11a. Okay, now in a solid, you know, the particles vibrate to and fro. They are fixed in position. If you remember the properties of solids, liquids and gases, solids, they have their particles in fixed positions, so they move back and forth. So that vibration is a simple harmonic motion. Let's look at figure 19.11a over here. See, we can think of the bonds between atoms as being springy. This leads to vibrations, A in a molecule of hydrogen and B in a solid crystal. So here also vibration back and forth, here in a solid also back and forth. Now here hydrogen is a gas, by the way. So if it's a gas, also it applies. Hydrogen molecule, yes. So in the molecule also that's what's happening. Okay, so that's the end of that page. Now oscillations can be very complex with many different frequencies of oscillation occurring at the same time. Examples include the vibrations of machinery, the motion of waves on the sea, and vibration of a solid crystal formed when atoms, ions or molecules bond together. Like for example over here, figure 19.11b, that is this one. It is possible to break down a complex oscillation into a sum of simple oscillations, and so we will focus our attention in this chapter on simple harmonic motion, SHM, with only one frequency. Okay, because we have several frequencies, it's complicated. We will also concentrate on large scale mechanical oscillations. Now, this is very small, so we will think of large scale ones like this one or this one. Okay, or maybe even this one. But you should bear in mind that this analysis can be extended to situations mentioned above and many more besides. So what was mentioned above was what we saw earlier, okay, these examples, but this is on a very small scale, okay, atomic, the size of atom or electron, these ones. So here I told you about the equilibrium position for a pendulum, that is when it is in the vertical position and where it comes to rest after oscillating. The swinging pendulum has positive displacement x and negative velocity y. So to the right side we took it as positive, so anything to the left direction is negative, so that's why the displacement is positive. Now even if it is over here, still the displacement is positive because it is to the right of the equilibrium position, but the velocity, because it's moving this way, will be negative. Now if this pendulum was moving to the right of the equilibrium position, it's moving to the right of the equilibrium position and it is also moving upwards, okay, moving this way, then the displacement is positive, the velocity also will be positive because it's okay, in the beginning it's here and it goes like this. So as soon as it passes this equilibrium position, and if it's moving to the right, the displacement is positive and also the velocity is positive. Now over here in this example, what is happening is it's moving to the left, but it is on the right side of the equilibrium position. So over here the displacement will decrease and the velocity will increase, because over here at the extreme end the velocity is 0, and then when it comes to the equilibrium position from the extreme end, we learned previously that the velocity is increasing because it's accelerating, the force is increasing, the resultant force is increasing, displacement is decreasing. Okay, then changes of velocity in simple harmonic motion. As the pendulum swings back and forth, its velocity is constantly changing as it swings from right to left, as shown in figure 19.12. Okay, I already explained this. Its velocity is negative. It accelerates towards the equilibrium position. Speed is increasing to the equilibrium and then decelerates as it approaches the other end of the oscillation. So it slows down as it reaches the other end of the oscillation, because it has to slow down and come to rest there again, and then it comes back this way and the process continues. It has positive velocity as it swings back from left to right again. Okay, so when it goes back this way, the velocity is this way, but the displacement is negative. So velocity continues to be positive until it comes to the other extreme point. So from this extreme point to the next extreme point, the velocity is negative. But from this extreme point, when it goes to the other extreme point, the velocity is positive. It has positive velocity as it swings back from left to right. From left to right. It has positive velocity as it swings back from left to right. Again, it has maximum speed as it travels through the equilibrium position. Okay, I already taught you all this. And decelerate as it swings up to its starting position. So when it goes towards the extreme point from the equilibrium position, it decelerates. I have taught you all this before in the beginning of this lesson. When it came to the trolley, I already explained all this. Now we are applying it to the pendulum. This pattern of acceleration, deceleration, changing direction, acceleration again, is characteristic of simple harmonic motion. There are no sudden changes of velocity. That's why I told you that sawtooth diagram is incorrect, because there you got a sudden change. So it can't be like this, it has to be this graph. There are no sudden changes of velocity. In the next section, we will see how we can observe these changes and how we can represent them graphically. Okay, so again here are some more questions. Okay, so we'll go through this. I already have explained this. Now figure 19.3, that is for the trolley. Identify the features of the motion of the trolley in figure 19.3 on page 287 that satisfy the three requirements for simple harmonic motion. Okay, so Oh, by the way, we missed this part. Okay, we'll go through this part also. I explained this and then I explained this one. I think I forgot to explain this. Okay, we'll go through this one quickly. It's very important but very short. If a simple pendulum is undisturbed, it is in equilibrium. Okay. So for example, if you look at this pendulum, if it's in the vertical position, it will remain like that. It's undisturbed, so it is in the equilibrium position. Or we can also say, if this is swinging and then it's let to swing, okay, freely oscillating due to friction, due to air resistance, and also due to friction over here where the pendulum is attached to this roof or whatever place, there's friction there, and also there's friction due to air resistance. So because of that we have damping, and because of damping the amplitude will decrease and become 0. That is when it will be at its vertical position. So that is the undisturbed or rest or equilibrium position. If a pendulum is undisturbed, it is in equilibrium. Okay, equilibrium, why? Because the forces are balanced. Now when this pendulum is in the vertical position, the weight force is equal to the tension in the string. So the forces are balanced, it is in equilibrium. If a pendulum is undisturbed, it is in equilibrium. The string and the mass will hang vertically. To start it swinging, it must be pulled to one side of its equilibrium position. The forces on the mass are unbalanced, and so it moves back towards its equilibrium. The forces on the mass are unbalanced, so it moves back towards its equilibrium. Now over here you can see the weight is vertically downwards. This is the tension is this way. The two forces are not equal. Okay, as a result it will accelerate because there is a resultant force. If the forces are balanced, no resultant force, but if the forces are unbalanced, there will be a resultant force. To start its swinging, it must be pulled to one side of its equilibrium position. The forces on the mass are unbalanced, and so it moves back towards its equilibrium position. The mass swings past this point and continues until it comes to rest momentarily at the other side. The process is then repeated in the opposite direction, so it moves backwards, forwards like that. Note that a complete oscillation in figure 19.12 is from right to left and back again. Okay, so let's say if you start from here, right to left, okay, that is one oscillation. Okay, or if you start here, then if it's moving this way, so right to left and then back to this position. So you can even start the oscillation over here. Normally in the case of a pendulum, we keep the fiducial mark or pointer right below the pendulum, and then as soon as it passes this point we start timing. So it goes like this. That is one oscillation. So again, so the pendulum is going like this, and then at this point we start the time. So it goes like this, and then comes back to the same position. That is one complete oscillation. So that's what they mean by this sentence. Okay, so here are the requirements for simple harmonic motion. It is very important that you know these 3 points. The 3 requirements for simple harmonic motion of a mechanical system are: a mass that oscillates, a position where the mass is in equilibrium. Conventionally, displacement x to the right of this position is taken as positive, to the left is negative. I already explained this. Okay, so for simple harmonic motion there has to be a mass that is oscillating, and then there has to be where the some position where the mass is in equilibrium, and to the right of this position we take as positive displacement, to the left we take as negative displacement. Then the restoring force. Now this is the resultant force. Why it's called restoring? Because it tries to bring the mass to the equilibrium position. So the restoring force or the resultant force is always towards the equilibrium or rest position. Okay, you know the meaning of the word restoring. Restoring means it tries to bring it to equilibrium. It tries to restore it. Okay, bring it to the undisturbed or equilibrium position. A restoring force that acts to return the mass to its equilibrium position. The restoring force F is directly proportional to the displacement x of the mass from its equilibrium position and is directed towards that point. Okay, so again you can see over here the greater and greater the displacement from the equilibrium position, the greater and greater will be the resultant force. So the greater the resultant force, the greater the displacement, greater the resultant force. For example, if you consider the example of this spring mass system, the trolley, okay, we call this a spring mass system. If you look at the spring mass system, when the more and more you pull it to one side, the greater and greater will be the extension of one spring, and greater will be the compression of one spring. And you know, according to F equals kx, greater the x is the compression or extension, greater the x, greater will be the force from the spring. Okay, so that's why so we can apply it to this here. Okay, the restoring force is directly proportional to the displacement x of the mass from the equilibrium position and is directed towards that point. That point means it's directed towards the equilibrium position. Again, I already explained it. Now if this trolley is to the right side, this spring is compressed, this spring is extended, so the force from both springs will be to the left. And if the trolley was on this side, this spring is compressed, this spring is extended, both forces will be to the right. Okay, so always the force is directed towards the equilibrium position. Okay, so I hope that is clear. Now we'll try to answer this question. Identify the features of the motion of the trolley in figure 19.3 that satisfy the three requirements for simple harmonic motion. So we have a mass that oscillates, which is the mass of the trolley, and position where the mass is in equilibrium, that is in the middle. Okay, and to the right we take as positive, to the left we take as negative. So for this, okay, they're asking. Then restoring force, I already explained that. Okay, let's look at the answer. Which question is this? Question number 5. Did we miss question number 4? We'll go back to question number 4 afterwards. Okay, the trolley is the mass. The central position of the trolley is the equilibrium position. The resultant restoring force of the springs is the force. So very easy. Okay, sixth one. Explain why motion of someone jumping up and down on a trampoline is not simple harmonic motion. Their feet lose contact with the trampoline during each bounce. So in the case of a person jumping up and down, one thing is now he okay, so first thing is we have the mass. Okay, we have a mass, but look at this. Okay, so over here in this case, now when the person is jumping up, okay, so we can take up as positive, down as negative, but the restoring force is always, in the case of a person jumping, the restoring force we can say is the weight. Now that weight is always directed downwards. Okay, and it is not directly proportional. Now the more and more the child goes up, his weight won't be greater and greater. It's a constant. So the force is not directly proportional to the displacement. Let's look at the answer. The restoring force is not proportional to the distance from the equilibrium point. When the person is not in contact with the trampoline, the restoring force is equal to the person's weight, which is constant. Very easy. Okay, we missed one question. That was question number 4, I think. Let's check that now. Okay, over here. Okay, figure 19.9b. Okay, 19.9b shows two oscillations which are out of phase. By what fraction of an oscillation are they out of phase? So it's half a wave. Half a wave means 90 degrees. Sorry, 180 degrees. Okay, half an oscillation or 180 degrees, or also we can say pi radians. 180 degrees or pi radians, or half an oscillation. Why would it not make sense to ask the same question about 19.9c? Here they have different periods or different frequencies, so we can't say by how much of an oscillation. So if they are to by how much of an oscillation, they have to have the same frequency. The waves have different frequencies, so the phase difference is changing continuously or continuously changing. I hope that's clear. Okay, we can't apply it for this because we can't get a phase difference here because it's changing all the time, because they have different frequencies. Okay, so the next one is representing simple harmonic motion graphically. Now you can see the spring mass system. If you set up a trolley tethered between springs, here here are two sets of springs. Figure 19.13. A motion sensor can be used to investigate simple harmonic motion of a spring trolley system. Okay, we can also call, the trolley has a mass, so we can also call this spring mass system. Now you can see there is a card on top. Whenever you get a diagram or whenever you get a graph, have a good look at it. Make sure you understand as much as possible of the diagram or graph. In this case, you are given a diagram, a figure. So try to understand as much as you can. Look at all the labels, look at what is given there, and try to understand as much as possible of this diagram. And when you read about it also, you can look at the diagram so that you can have a good understanding of what this diagram is about. Okay, a motion sensor can be used to investigate simple harmonic motion of a spring trolley system. Okay, spring. So here the springs, and this is the trolley. So we can also call this spring mass system. And here we have a motion sensor. I have explained to you previously that the motion sensor should be placed along the direction of motion of the object. So if you want to use the motion sensor for a particular object that is moving, that motion sensor should be kept along the direction of motion. Now in this case, the trolley is moving in this direction, right, back and forth. So the motion sensor should be placed in the direction of motion, or along the direction of motion, which is this way. So this is correctly fixed. Now you can see there is also a card attached to the top. The purpose of the card is so this motion sensor will give out waves. So the waves get reflected and then come back to the motion sensor. Now if there was no card, then these waves cannot strike the surface of the trolley easily. Okay, so the card is fixed to the top of the trolley. This sends waves and this detects. So once it sends and detects, it is connected to the computer, so the computer can draw the displacement time graph, velocity time graph, and acceleration time graphs. Alright, so now you understand how this motion sensor can be used for this kind of example. If you understand this motion sensor, you can apply for any example also. Now even in the AS classes, I think it was in chapter 1, there was an example of a motion sensor. Okay, so here again you see it, but I explained in more detail. There you didn't have these graphs like this, but here we have the graphs. Okay, so if you set up a trolley tethered between springs, you can hear the characteristic rhythm of simple harmonic motion as the trolley oscillates back and forth. By adjusting the mass carried by the trolley, you can achieve oscillation with a period of about 2 seconds. Now what happens is you can add masses to this. Maybe you can tape slotted masses to this and adjust the mass of this trolley, so that you get a oscillation that is about 2 seconds, having a period of about 2 seconds. Because if it is too light, then it will oscillate too fast. If it is too heavy also, it will oscillate too slowly. So you can adjust the mass on the trolley so that you achieve oscillations with a period of about 2 seconds. The motion sensor allows you to record how the displacement of the trolley varies with time. Okay, so that is, here we have the graph for that. Ultrasonic pulses from the sensor are reflected by the card on the trolley, and the reflected pulses are detected. So this is what I said. So it gives ultrasound waves. You know, sound waves. We have infrasound, ultrasound, and what we can hear is what is in the audible range between 20 Hz and 20,000 Hz. The ultrasound is having a frequency greater than 20,000 Hz or 20 kilohertz, which are frequencies above our audible or hearing range. Okay, so we will not be able to hear this sound. Okay, so it's giving out sound waves, ultrasonic pulses, which we can't hear. But if there was an animal like a dolphin or a creature that can hear this, it will be able to hear it. But anyway, this is out of this particular topic. Okay, ultrasound pulses from the sensor are reflected by the card, so it reflects by the card on the trolley, and the reflected pulses are detected. So it comes back to this sonar technique. Okay, so these are called sonar technique, allows the sensor to determine the displacement of the trolley. A typical screen display is shown in figure 19.14. Figure 19.14 over here. Okay, this is connected to the computer, motion sensor connected to the computer, so you will get something like this. Now you can see the displacement, the amplitude decreases with time. Because of friction there is damping, so the amplitude becomes less and less, and finally it stops. So this is what you get. Okay, so very important. Okay, this is extremely important. Maybe in other experiments also they can ask you how to use that motion sensor. So you have to say this is what we do, and this is the graph you are getting. Remember, the motion sensor is placed along the direction of motion of the object. It sends out pulses of ultrasound and then detects them. So if it has to be like this, so that the placed like this, so that pulses go, hit and come back. Okay, and this technique is the sonar technique. Okay, the computer can then determine the velocity of the trolley by calculating the rate of change of displacement. Similarly, it can calculate the rate of change of velocity to determine the acceleration. So I said this is connected to the computer. So once you have this, the computer can then draw this graph and also this graph, velocity time graph and acceleration time graph can be drawn from the displacement time graph. See, that's what they say here. Idealized graphs can be graphs of displacement, velocity and acceleration against time are shown in figure 19.15. So the three figures over here. We will examine these graphs in sequence to see what they tell us about simple harmonic motion and how the three graphs are related to one another. Okay, a typical displacement time graph generated by a motion sensor. So this is generated by the motion sensor, and here using the computer we can get these other graphs. Okay, so we are going to learn about these three graphs now. Okay, it's very similar to what it's actually I have already explained this part to you when I was explaining the spring mass system earlier. Graphs of displacement x, velocity v and acceleration a against time t for simple harmonic motion. Okay, so you can see over here again they start timing as soon as the trolley moves to the right of its equilibrium position. So to the right the displacement is increasing and becomes maximum. Okay, that is when it is at the extreme right end over here, somewhere here. So there the displacement is maximum and positive 0.02 meters. Then it moves to the left like this and comes to this position. Okay, so there the displacement is again 0. Okay, so from here to here displacement is 0. Then it moves to the left like this. So from here to here, that is from here to the left extreme end. Then from here to here, so from here it goes over here. Okay, that is for this part of the motion, and this process continues. Okay, so it goes and then comes back, and then again it continues like this. Okay, so we have a displacement time graph, period, amplitude, all of that is indicated over here. Period is the time for one complete wave. Okay, so you can see if it starts at this end, goes like this, and over here, so that is one whole cycle, one whole period. Okay, we can even start from here, goes like this and comes back to this position. That is also one time for one complete wave, which is the period. Okay, so from this gradient of this graph, gradient of a displacement time graph gives you the velocity. So you can get the velocity from this graph by calculating the gradient. The computer does that. Velocity is rate of change of displacement. You can see over here the velocity is 0, which corresponds to that point. See, velocity is 0 at this point. Now from here to here you can see the velocity is positive and decreasing and becomes 0. Velocity is positive, decreasing and becomes 0. So positive, decreasing and becomes 0. Then from here to here the velocity is negative, decreasing and becomes 0. Sorry, and becomes maximum. So from here to here the velocity is 0, negative, and increasing. 0, negative and increasing and becomes maximum. So 0, negative and increasing. Can you see the negative value is increasing? the velocity negative and increasing and becomes and becomes maximum. Yes, and becomes maximum. So velocity is 0, it's negative and increasing and becomes maximum. 0, negative and increasing and becomes maximum. Okay, then after that what happens is the velocity over here is we'll look at this graph. Okay, so here it's maximum, you can see here. So at 0.2 seconds it's maximum. Then what happens from here to here, looking at this graph, the gradient becomes less and less and less negative and becomes 0. So less and less and less negative and becomes 0, and again the process continues after that. Okay, so over here also we can see from here to here the velocity 0 becomes more and more positive and reaches the maximum value. 0, more and more positive and reaches the maximum value of velocity. Okay, so if you look at okay, so at this position the velocity is 0, at this position the velocity is 0. So these are the positions where the trolley is at the extreme ends, and here and here and also here, those are the positions where the trolley is at the equilibrium position, that is in the middle of the oscillation. Sorry, it's in the middle. Okay, middle over here in the center point, it is at the center. So where the velocity is maximum positive or negative is where the trolley is in the middle or at the equilibrium position. Now from the velocity time graph you can get the acceleration time graph, get the gradient of this. Gradient here is negative and increasing. Okay, so up to 0.1 it's negative and increasing, and then from 0.1 to 0.2 it's still negative but decreasing and becomes 0. Okay, so from 0.1 to 0.2 the gradient is negative, decreasing and becomes 0 for this graph. Okay, so you see acceleration is the gradient, so gradient decreasing and becoming 0 means acceleration decreasing and becomes 0. Then after that the acceleration, here you can see acceleration is 0 because gradient is 0. Then a gradient becomes more and more and more positive and becomes a maximum value. So becomes more and more positive and becomes a maximum value, acceleration maximum. Then from here to here gradient becomes less and becomes 0. Acceleration becomes less and becomes 0. Okay, so acceleration becomes less and becomes 0. So the process continues. Okay, so you can also go through this by yourself, so you'll have a better understanding. It's very important that you understand these graphs. In the AS classes also you have seen these kinds of you have seen displacement time graphs and how to get the velocity and acceleration time graphs. Okay, so you can see the acceleration. Okay, one more point, very important. The acceleration is maximum when the displacement is maximum, positive or negative, because the springs are compressed or extended maximum at the extreme points where the velocity is 0. So when the velocity is 0 there is an acceleration. Okay, so even though this is at a momentary stop, the speed is 0, still there is an acceleration. Okay, and the acceleration is maximum when the velocity is 0. Alright, so there are instances where there is an acceleration when the velocity is 0. For example, if you throw a ball up at the highest position, the ball has a acceleration, which is the acceleration of free fall, that is vertically down. So the ball comes to a momentary stop at the highest position. The velocity is 0 at the highest position. When you throw a ball vertically upwards at the highest position, the velocity is 0, but still the ball has a acceleration 9.8 vertically downwards. Okay, so similarly over here, even though it comes to a momentary stop, there is an acceleration, and the acceleration is maximum there because the resultant force is maximum. We will go into more detail about these graphs because it is extremely important. If you look at the displacement time graph, from this you can find the period. Okay, if you start here, you complete one wave and then you end here. So the period is 0.4 seconds. and also you can find the amplitude. Okay, amplitude is the maximum displacement. We can also say it is the maximum height of the crest or the trough, and it is about 0.02 meters. You can see the unit on the y-axis is meters, so 0.02 meters. And one more thing is, we have taken to the right of the equilibrium position as positive, and we have started timing when it passed the equilibrium position and is to the right. So when it was at the equilibrium position, we started the timing. You can see the time starts at 0 when the displacement is 0. Displacement is 0 at the equilibrium position. Okay, and you can see the displacement is increasing with time. That means it is moving to the right from the equilibrium position when the starting from time t equals 0. Now if you started the time when it was at one extreme end, either to the left or to the right, then this will not start at 0. It will start at 0.02. The graph will start at 0.02 if you start at the extreme point, because it already has the maximum displacement when you start the timing. Okay, if you start like this you can see is a sinusoidal graph. That means it is in the shape of a sine wave, and when time is 0, the displacement is 0. Therefore this is a sine graph. You can see in a sine graph also, you have learned for mathematics that it passes through the origin, whereas the cosine graph, like what you see here, will not pass through the origin. So if it was this kind of graph, that means if you start the timing when it is at the equilibrium position, that means t is equal to 0, when the displacement is equal to 0, then the equation of this graph will be this one: x equals x naught sine omega t. Now we will go into the details afterwards. Remember, if it starts at the origin, it is a sine graph. If it doesn't start at the origin, if it already has a maximum displacement like this, okay, it's shown here. See, if it's like this, then it will be a sine graph. If it starts like somewhere there, if it already has a displacement when t is equal to 0, it will be a cosine graph. Okay, so you have to know that. All right, let's go back to the graphs. Okay, so this is what they are explaining, what I explained just now. By the way, x naught is the maximum displacement, that is the amplitude. We saw that in the equation of the graph also. X naught over here, that is the maximum displacement, which is the amplitude. Okay, in this graph, okay, the displacement x of the oscillation is shown at 0 at the start when t is 0. We have chosen to consider the motion to start when the mass is at the midpoint of the oscillation, equilibrium position, and is moving to the right. We could have chosen any other point in the cycle as the starting point, but it is conventional to start as shown here. So this is the standard, or it is conventional, we can say. And you know, from the gradient of a displacement time graph, we can get the velocity time graph. So this is the velocity time graph for this motion. Now for this, we learned earlier, for this apparatus, this system, this is the displacement time graph, this is the velocity time graph, and this is the acceleration time graph. And we learned how to go from the displacement time graph to the acceleration velocity time graph, and from the velocity time graph to the acceleration time graph. And you can see that over here, this is a like a cosine graph, because it already has a value when x is 0, sorry, when t is 0, when the value on the x-axis is 0, it already has the maximum value on the y-axis. Okay, so this will have the equation of a cosine graph. Now you know, when you differentiate displacement, you will get velocity. Okay, so for those students who are taking mathematics will understand this easily. If you who have learned differentiation, differentiation is similar to finding the gradient. Okay, so when you differentiate, you're actually getting the gradient of that graph. So here we have for displacement, and if you get the gradient, that is the same as like differentiation. If you differentiate it, what you will get is cosine. So if you differentiate this, you will get cosine, and x0 is the amplitude, it doesn't change. Omega is what we will learn that. Okay, and t is the time. Okay, omega is also a constant, and here it's given omega is its frequency. Okay, angular frequency. So frequency of movement. Okay, so that is also constant. Therefore, when you differentiate this, you will get this, and if you differentiate this, you will get the acceleration. Now there is a mistake here. This should not be x, it should be v. Okay, v equals x0 cosine omega t, and you can differentiate this. Here is a mistake. Okay, it should be, you can cross that out and write v there in your book. Okay, v. So what happens is, again, if you differentiate this, the velocity versus time graph, if you get the gradient, you will get the acceleration. So if you differentiate this, the function of velocity, you will get the function for acceleration. Okay, so we will see those derivations soon, but we'll first finish this off. So here all these graphs are sinusoidal because they take the shape of a sine graph. So you see, its variation is described as sinusoidal. And also about the velocity time graph, I explained previously, the maximum velocity is at the equilibrium position. You can see over here, this is the equilibrium position. The displacement is 0 there. Similar, and the time was also 0 when displacement is 0. So similarly, you can see here, when the time is 0, the velocity is maximum, because the velocity is maximum at the equilibrium position, and velocity is 0 at the extreme ends. You can see here the displacement is maximum, and when the displacement is maximum, the velocity is 0. Alright, then the last part is about the acceleration time graph. Okay, you know, acceleration is change in velocity over time, and according to the definition of simple harmonic motion, we learned that the acceleration is proportional to the displacement, but is in the opposite direction to increasing displacement. So if the displacement is increasing to the right, acceleration is to the left. Okay, that's what is explained by this, and that's the reason the direction is opposite, so you have the negative sign. Okay, we'll go through this quickly. This gives a third curve of the same general form, which shows how the acceleration A depends on time t. At the start of the oscillation, the mass is at its equilibrium position. There is no resultant force acting on it, so its acceleration is 0. Okay, so at the equilibrium position, I have explained previously, the forces are balanced, so the resultant force is 0. Therefore, at the equilibrium position, which is when the time is 0, the acceleration is 0. Alright, then as it moves to the right, the restoring force, you know that the restoring force is always directed to the center. It is the resultant force on the mass, on the trolley. It is directed towards the center or middle of the oscillation. It is directed towards the equilibrium position. Okay, it's called restoring force because it tries to bring it to the equilibrium position. So that's why the word restoring is there. So when the object is moving to the right, when the trolley is moving to the right, the restoring force acts to the left, giving it a negative acceleration. Okay, so when acceleration is to the left, it's a negative, because whatever is to the right we took as positive, to the right we took as positive by conventional way. The acceleration has its greatest value when the mass is displaced furthest from the equilibrium position. Okay, we can also see that from the graph. When the displacement is maximum, you can see the acceleration is maximum negative and maximum positive. See, when the displacement is maximum, acceleration is maximum. Magnitude of the acceleration is maximum. Okay, notice that the acceleration graph is upside down compared to the displacement time graph. This shows that acceleration is proportional to the negative value of the displacement, or acceleration is proportional to minus x. X is the symbol we use for displacement. A is the symbol we use for acceleration. Okay, finally I already explained this. In other words, whenever the mass has a positive displacement to the right, its acceleration is to the left, and vice versa. You can see this is like the upside down of this displacement time graph. You can see here, when this is up here, this is down there, and this is down here, this is up there. Okay, so that is about displacement time, velocity time, and acceleration time graphs for objects in simple harmonic motion. Then you have to know this equation. Okay, then here we have f here. Frequency f of simple harmonic motion is equal to the number of oscillations per unit time. As we saw earlier, f is related to the period t by this. Okay, so you have to be familiar with this f and the other f, angular frequency, which is omega. Okay, we will see that afterwards. Now you can see omega is angular frequency. When you learned about circular motion, you learned that this omega is the angular speed. Okay, omega is the angular speed in circular motion, but in simple harmonic motion we call this the angular frequency. Same symbol is used but two different names. Here angular frequency, in circular motion it was the angular speed. Okay, now you know for one whole wave we can take it as 2 pi radians. So similarly we can think of a complete oscillation of an oscillator or a cycle of simple harmonic motion as being represented by 2 pi radians. This is similar to a complete cycle of circular motion, where an object moves round through 2 pi radians. The phase of the oscillation changes by 2 pi radians during one oscillation. Hence, if there are f oscillations in unit time, there must be 2 pi f. Now what we can also do is we can replace the t with 2 pi over okay, you know the formula, f is equal to 1 over t, and for this we can substitute see 2 pi. Okay, they already have it here. T is equal to 2 pi over omega, or omega equals 2 pi over t. Okay, but before that we'll see this one. The phase of the oscillation changes by 2 pi radians during one oscillation. So one oscillation, one complete cycle is 2 pi radians. Hence, if there are f oscillations in unit time, there must be 2 pi times f radians in unit time. This quantity is the angular frequency. So this is omega equals 2 pi f. Okay, so we have this. Okay, this is the angular frequency of the simple harmonic motion. So again, 2 pi is for one whole cycle, and in if there are f number of oscillations, then it's 2 pi f in unit time, and it is represented by the angular frequency omega is thus related to the frequency f by the following equation. Since f is equal to 1 over t, the angular frequency omega is related to the period t of the oscillator by the equation. So for f we can substitute 1 over t, then we get 2 pi over t. So you have to know this equation also. You have to know this one, then from this you can figure out these two. So very important, you can note this down. This is the other equation you have to know. Omega equals 2 pi f. So all these equations are very important. You have to be able to figure out which equation you are supposed to use when you get a simple harmonic equation. So what you can do is you can have all the equations that you learned written down, and over here remember, if you are using the sine, if it's a sine graph, then it should have sine in the equation. If it's a cosine graph like this, it should have cosine in the equation, like what I showed you here. Okay, see here it's sine because that's from the origin, it passes through the origin. Here it's a cosine because it doesn't pass through the origin, and it has a maximum value when the value on the x-axis is 0. The y-intercept is maximum. Okay, so there are some questions over here, very important that you do them. We'll go through this bit also. In figure 19.17, a single cycle of simple harmonic motion is shown, but with the x-axis marked with the phase of motion in radians. Okay, you can see that here for one whole cycle it is 2 pi radians. Half a cycle is pi radians. So phase in radians. Here is the displacement. X0 is the maximum displacement. So we have positive displacement and negative displacement. The phase of an oscillation varies from 0 to 2 pi during one cycle. 0 to 2 pi during one cycle. Okay, let's see this last bit. Okay, so then about the equations of simple harmonic motion, the graph of figure 19.15, let's see that graph 19.15. yeah, these graphs, okay, they are referring to the graphs we were discussing about earlier. The graphs of figure 19.15 as shown earlier represent how the displacement of an oscillator varies during simple harmonic motion. We have already mentioned that this is a sine curve. We can represent the same information in the form of an equation. The relationship between the displacement x and time t is as follows. X equals x0 sine omega t, where x0 is the amplitude of the motion and omega is the frequency. Now it's actually there is a mistake here. It should not be just frequency, it's angular frequency, because f we use for frequency. Simple f is the symbol for frequency, but omega is the symbol for angular frequency. So here it should be, so you can add it to this. There's a mistake here. So what you do is you correct it in your book, add the word angular frequency. Okay, in pencil you write over there angular frequency, where x0 is the amplitude of motion and omega is its angular frequency. Sometimes the same motion is represented using a cosine function rather than a sine function. Oh, sorry, by the way, this is not the sorry, you can leave it like this. This is correct, because I thought this is for the velocity, but once you differentiate this, you will also get a omega. See, if you differentiate this, you will get x0 omega cosine omega t. So what they are explaining over here is sorry, this is not the velocity time graph, this is all still the displacement time graph. Okay, so if you start timing so this is a displacement versus time graph. So if you start timing when it is at the equilibrium position, now over here the timing has started when it is at the extreme end on the right side, at the extreme end. Okay, so what happens is it moves to the left, so the positive displacement decreases, and then it is still moving to the left. Now here it is at the equilibrium position, it still moves to the left and reaches the other extreme end, which is on the left side. And then what happens, you can see from here to here the gradient is negative because the velocity is to the left. Then afterwards it moves to the right. Now it is here at the extreme left end, then after that it reverses the direction, it moves to starts moving to the right now. So from here to here it's moving to the right and it reaches the equilibrium position, and then from here to here it's still moving to the right of the equilibrium position now, and it moves and it reaches the extreme right end. Okay, so the process continues. Okay, so if you start the timing when the displacement is maximum, then you will have this equation. If you start when the displacement is 0, you will have this equation, because you can see this is a sine graph. Sine graph passes through the origin. Here it's a cosine graph. Cosine graph has maximum value of y or y-intercept or displacement when the time is 0. Okay, so remember the only difference here is over here you start timing when the displacement is 0, and over here you start timing when the displacement is maximum. Okay, so this is fine, this is correct. Okay, but over here omega should be angular frequency. Okay, we can see the derivations for these graphs also. The difference between these two equations is illustrated in figure 19.19. The sine version starts at x equals 0, that is the oscillating mass is at its equilibrium position when t equals 0. Okay, so the oscillating mass is at the equilibrium position when t is equal to 0 over here. These two graphs represent the same simple harmonic motion. The difference in starting positions is related to the sine and cosine forms of the equation for x as a function of it. Okay, so the cosine version starts at x equals x naught, so that the mass is at its maximum displacement when t equals 0. Note that in calculations using these equations, the quantity omega t is in radians. The angle is in radians. Make sure your calculator is in radian mode for any calculation. See worked example 2. The presence of the pi in the equation should remind you of this. Worked example 2 is over here. Okay, so remember this omega t, you can use a bracket here. Always use a bracket, then it will avoid confusion. Now when you are entering in the calculator also, you are supposed to use a bracket over here and another bracket over here. So after the sign, quickly, right after the n sign and letter n of sign, you have to open a bracket, and after the t you have to close a bracket. So put the omega t in parentheses always. Okay, now okay, we can go through these examples also. Okay, before that I'll show you the differentiation to get these equations, but here we don't have the velocity equation, right? I think it's coming up later. Yes, see, this was what I wanted to mention. Okay, yeah, there is no omega bit. Yeah, best thing is we'll derive it, then no confusion. Okay, so cosine omega t, yeah, so there is no omega here. All right, what I mentioned was if it's velocity, I accidentally said that there will be omega multiplying it, but omega is not multiplying it. You can see over here. So best thing is we can do the derivation we can differentiate it and get the derivative. We can get the derivatives and we can check our work. Okay, before that we'll okay, so what we can also do is we can quickly go through these examples. Okay, there are a lot of questions. I think you are able to do them. We'll see. Question number 7. Use the graph shown in figure 19.15 to determine the values of the following quantities: amplitude, period, maximum velocity, maximum acceleration. Very easy. So let's go up there and have a look. I think we already saw it before. Here it's 0.02 and the period is from here to here, 0.4 seconds. You are right, did it. We'll look at the answers also. 0.02 and the period is 0.4. Maximum velocity is 0.3 meters per second, 0.31 meters per second. You have to look a bit closely, look at it carefully, because if you are half a square off also you can lose the mark. Yes, 0.31. It goes a little bit below 0.3, so here 0.31, 2, 4, 6, 8, 10. Yes, so 0.3. This is 0.32. Yes, 0.31. Then maximum acceleration. Maximum acceleration, you can see here 5 meters per second squared. Okay, let's go back to the questions. State at what point in an oscillation the oscillator has zero velocity but positive acceleration. So that is at the extreme ends. Now positive acceleration means the acceleration should be to the right. Now acceleration is always towards the rest position, so that means the object should be at the far at the extreme end on the left side, because when it is on the left side, the acceleration is to the right. Always the displacement and acceleration are opposite in direction. Okay, so it has to be at the extreme end on the left side, at the extreme left of the oscillation, that is maximum negative displacement. The acceleration is positive towards the right. Okay, I think it's clear. Okay, so imagine if it should be like if it's a pendulum or if it's the spring mass system. Okay, this should be on this side over here, because when it is over here on the far left end, the acceleration is to the right and the velocity is 0. Okay, look at the graph. At the xt graph, look at the xt graph of figure 19.15a. There is a displacement time graph. When t is equal to 0.1 seconds, what is the gradient of the graph? State the velocity at this instant. So when the time is 0.1 seconds, 0.1 seconds, this is 0. The gradient is 0. Okay, if you look at this closely, if you draw the gradient when the time is 0.1 seconds, the gradient is 0 and it corresponds to the velocity. The velocity is 0. State the velocity at this. So gradient is the velocity, so the velocity is 0. Okay, so 0 centimeters per, gradient is 0, therefore velocity is 0. 10th question. Figure 19.16 shows the displacement time graph for an oscillating mass. Use the graph to determine the following quantities: the velocity in centimeters per second when t is equal to 0, the maximum velocity, the acceleration in centimeters per second square when t is equal to 1.0 seconds. A displacement time graph for an oscillating mass. See question 10. Okay, so a part, we are supposed to find the velocity. Velocity when time is 0. Time is 0, so zoom in. When the time is 0, the velocity is 30 centimeters per second. This is a displacement time graph. So we are supposed to find the velocity. Now the displacement is 30 when the time is 0, but here we are supposed to find the velocity. So gradient of the velocity time graph, gradient of the displacement time graph will give us the velocity. So the gradient at this point is 0. That means the velocity is 0 centimeters per second. See, 0 centimeters per second. Okay, the maximum velocity in centimeters per second. Maximum velocity will be the gradient of this curve when the time is 1.0 seconds. So you have to draw tangent like that and find the gradient of that tangent. Okay, the maximum gradient for this curve will be the maximum velocity. So you will have to draw a tangent like this. Okay, or maybe even here, but I think it's easier to draw it over here. It has to touch the curve at when the time is 1.0 over here. Okay, or over here also you can do, but better to do it here. Then you find the gradient of that tangent. It will be about 47 centimeters per second. Then the last part, the acceleration in centimeters per second squared when time is 0. When time is 0, when time is 1.0. When time is 1.0, it is at the equilibrium position. See, the displacement is 0, and when the displacement is 0, the resultant force is 0. Therefore, the acceleration is 0. Okay, that's the answer. Now we can go through the other questions also. We'll quickly finish it off. An object moving with simple harmonic motion goes through 2 complete cycles in 1 second. Calculate the period. So 2 complete cycles in 1 second. Okay, the frequency is 2 Hertz, because frequency is number of cycles per second. Okay, so 2 complete cycles in 1 second means the frequency is 2 Hertz. Then period is 1 over the frequency. Okay, or we can say period is the time for 1 complete cycle. Now 2 complete cycles 1 second, 1 complete cycle is therefore 0.5 seconds. So the period is 0.5 seconds. Okay, t is equal to 1 over f, and then frequency is 2 Hertz. Okay, the angular frequency. Now don't confuse this with this one. In the glossary of your book, the meanings of these words are given. Now you saw that the angular frequency word previously was in green bold letters, so that means you have to know the meaning of it. Okay, here in the glossary it's given the angular frequency, the frequency of a sinusoidal oscillation expressed in radians per second. Angular frequency is omega equals 2 pi over t. Alright, so using that equation we can find omega, the angular frequency. This is a Greek letter called omega. Okay, so omega equals 2 pi f, or omega equals 2 pi over t. Substitute and we get so f is 2 into 2 4 pi radians per second. Remember, the unit is in radians per second. Okay, finish this off quickly. Figure 19.18 shows the displacement time graph for an oscillating mass. Displacement time graph for question 12. Use the graph to determine the following: amplitude, period, frequency, angular frequency, displacement at A, velocity at B, velocity at C. Okay, amplitude is the maximum displacement, and we can see over here it is 0.20, right? 0.20. That's the answer. 0.20, and write the unit also. This is in meters. Then period is the time for one complete wave, so that is 0.4 seconds. 0.4 seconds. 0.4 seconds. Then frequency is 1 over the period, so 1 over 0.4, which is 2.5 hertz. Alright, then angular frequency is 2 pi f. Okay, so substitute 2.5 for f, you get 2 times 2.5, which is 5, and the pi is still there, pi radians per second. Remember, the unit of angular frequency is radians per second. The unit of frequency is hertz. Then displacement at A. Now this is a displacement versus time graph. So the displacement at A is, you can see, negative 0.10 meters. Negative 0.10 meters. Velocity at B. Velocity at B, this is a displacement time graph. So the gradient of a displacement time graph gives the velocity. The velocity at B can be found by finding the gradient. And if you draw tangent at B, it will be a horizontal line. The gradient of a horizontal line is 0. Therefore, the velocity at B is 0. 0 meters per second. G part, velocity at C. Now over here, what you need to do is draw the tangent to the curve at C, find the gradient of the tangent, and you should get 3.1 meters per second. Okay, or else using the equation, but over here they didn't really teach you how to use that equation. Okay, you can use the equation for velocity. I'll show you. On this one, the velocity equation, because you know all the other quantities, so here you can use this equation. Okay, maximum velocity. Okay, but still you don't know the velocity, right? That's the problem. Velocity at C. At C it will be the maximum velocity, but even if you use this equation, don't think you can get it here, because here you are still getting the displacement. Yes, so you will have to find the gradient and do it that way. Alright, next question, number 13. An atom in a crystal vibrates with simple harmonic motion with a frequency of 10 to the power 14 Hertz. The amplitude of its motion is 2.0 into 10 to the power minus 12. Sketch a graph to show how the displacement of the atom varies during one cycle. Use your graph to estimate the maximum velocity of the atom. So you draw a displacement time graph and find the gradient where the gradient is maximum. That will give you the maximum velocity. Okay, now over here when you're sketching, you have to indicate certain things, like for example the here they have given us the frequency, so we can find the period. So you have to show the time for one complete cycle like this. What is the time there? And amplitude is the maximum displacement, so you have to show the maximum displacement also. Let's look at the solution. See, over here they have shown that the period is 1 second. Frequency is 10 to the power 14 hertz. Okay, not 1 second, 1 into 10 to the power minus 14, because frequency is 1 over period, then period is 1 over frequency, so it will be 1 over this, which is 10 to the power minus 14 when it comes up, 10 to the power plus 14 when it comes up. According to the rules of indices, it will be minus 14, so they have included it with it over here. So 1, and then here you can see the amplitude is 2 into 10 to the power minus 12, so 2 into 10 to the power minus 12. Okay, then gradient at steepest point giving approximately 1.3 into 10 to the power 3 meters per second. So you will find the gradient over here at 0.5 seconds. Okay, then that's the end of those questions. Now we'll go through this example also, but before that let's go through this bit. Okay, okay, so I'll show you how to derive this equation. Okay, and you have to know this also. Okay, previously we learned this. According to the definition of simple harmonic motion, we have this: acceleration is proportional to the displacement but in the opposite direction. So using that to convert a proportion to an equation, we have to add a constant, and that constant is omega squared. Okay, so in simple harmonic motion, an object's acceleration depends on how far it is displaced from its equilibrium position and on the magnitude of the restoring force. The greater the displacement, the greater the acceleration. In fact, a is proportional to x. We can write the following equation to represent this. Okay, so the constant of proportionality, like I said, is omega squared. Minus sign shows that when the object is displaced to the right, the acceleration is the direction of acceleration is to the left. So always the acceleration and displacement are in opposite directions, and acceleration is always directed towards the equilibrium position in the opposite direction to displacement. It should not be surprising that the angular frequency omega appears in this equation. So omega is the angular frequency. We learned that already. Okay, imagine a mass hanging on a spring so that it can vibrate up and down. If the spring is stiff, the force on the mass will be greater. It will be accelerated more for a given displacement, and its frequency of oscillation will be higher. Okay, so angular frequency we already learned that, and here they are giving an example. If you have a stiffer spring, the force will be greater, so it will accelerate more for a given displacement, and its frequency of oscillation will be higher. Okay, so here this helps us to define simple harmonic motion. The acceleration a is directly proportional to the displacement x, and the minus sign shows that it is in the opposite direction. Okay, let's go through this example. A pendulum oscillates with frequency 1.5 Hz and amplitude 0.1 meters if it's passing through its equilibrium position when t equals 0. So that means you have to use the sine equation, because the timing started when it is at the equilibrium position. Write an equation to represent its displacement in terms of amplitude x0. So this is the equation. Remember, it's a sine graph. Angular frequency omega and time t. So x equals x0 sine, and in brackets you can write omega t. Determine its displacement when t is equal to 0.50 seconds. Then let's do that. Okay, so this is what we have. Determine its displacement when t is 0.50 seconds. Time is 0.50. First we can find omega. We know the frequency 1.5 Hertz, so we can find the omega here. 2 times pi times 1.5, we get 3.0 pi. Substitute values into the equation. Now x0 also is given, that is the amplitude. So we know this, we know this, and then we can write the equation. Okay, so this is the equation: x equals 0.10 sine 3.0 pi t. Now for any time we can find the displacement, and we are supposed to find the displacement when t is 0.5. So here we substitute 0.5 there, and we get negative 0.1 meters. Okay, this means that the pendulum is at the extreme end. Now you can see the amplitude is 0.1. So here also we get 0.1, but it is on the extreme left end. Okay, the minus sign means that it is at the negative or left hand end, assuming you have chosen to consider displacements to the right as positive. Okay, if your calculation went like this, now here what has happened was yeah, you didn't have the calculator in the correct mode. So remember, your calculator should be in radian mode over here, because we are entering the angle here in radians. Okay, this 2 pi and all, that is to do with radians. So make sure your calculator is in radian mode. If your calculator is in degree mode, you won't get the correct answer. Okay, then previously I already explained what this is about simple harmonic motion. This definition is extremely important. Yeah, so again it's already explaining what I had explained before. Okay, so there are some important points here. So we learned another equation now, which is this one. Okay, so we got it from the definition. Acceleration is directly proportional to the displacement, but in the opposite direction. Okay, and we converted that. See, we converted this into an equation. The constant of proportionality was omega squared. So A equals minus x, proportional to minus x. Okay, so magnitude of the gradient of the graph A versus x, negative x, is omega squared. So if you plot a graph, okay, it's here. See, if you plot a graph of A versus x, the gradient will be minus omega squared. This means that the acceleration is always directed towards the equilibrium position. Okay, so you can see the magnitude of the gradient, that is minus omega square, that is omega square, the magnitude. Okay, so we don't consider the sign when we say the magnitude. The gradient is independent of the amplitude of the motion. This means that the frequency f for a period t of the oscillator is independent of the amplitude, and so a simple harmonic oscillator keeps steady time. Then this graph is very important. Acceleration versus displacement. It is drawn using this equation, and this is a constant. The angular frequency is constant, so you can see y equals mx, but the gradient is negative, so that's why we have drawn this way. Okay, if it was a equals plus omega squared x, then it will be this way, but because the gradient is negative, it is drawn this way. Okay, so you should know this, the angular frequency is constant, and that is what is explained over here. The gradient is independent of the amplitude of motion. This means that the frequency f or period t of the oscillator is independent of the amplitude, and so simple harmonic oscillator keeps steady time. Okay, then we have more equations. Again, all these equations are very important. Here is the equation for velocity. Now if you differentiate this equation, you will get this one. Okay, so students who have done mathematics will already know this. Okay, if you differentiate sine, you get cosine, and inside also when you differentiate, it will be 1. Okay, when you differentiate this, times it by 1, so it will be v equals sorry, it will be okay, we will do it and see. Okay, so we will see how to get this, then there is no confusion. Okay, but for now you can remember this one. Again, the students who have not taken mathematics don't need to know the derivation. Okay, you can directly remember the equation and apply it. Okay, okay, so we have this one. for velocity, again for simple harmonic motion. And here also it starts from the origin, because when it is at the origin, if the timing started, the velocity is maximum. So for the velocity it is a cosine graph, but for the displacement it is a sine graph. So that's what they mentioned here. So remember, this cosine is there for the velocity time graph, because the velocity is maximum when the time is 0. Okay, then then we have this one. Okay, here is another equation. Now you have to know this equation as well. Okay, so you should know this one. This equation can be used to deduce the speed of an oscillator at any point in an oscillation, including its maximum speed. Now omega is the angular frequency, v is the speed, x0 is the amplitude, x is the displacement. Okay, then we have this. Now when the speed is maximum, you will get this one. Okay, how we get this is okay, maximum speed of an oscillator. If an oscillator is executed in simple harmonic motion, it has a maximum speed when it passes through its equilibrium position. This is when its displacement x is 0. The maximum velocity is when the displacement is 0. So this term here becomes 0. X squared, x is 0, so this becomes 0. Then what happens is, it will be v equals plus or minus omega square root of x0 squared. Right? So square root of x0 squared is x0. So we get this. The maximum, this is when its displacement x is 0. The maximum speed v0 of the oscillator depends on the frequency f of motion and on the amplitude x0. Okay. Yeah, so we will get this then. Okay, so you can see v0 is proportional to x0. The greater the amplitude, greater the maximum speed. Okay, then also we can see this is also proportional to omega. From this equation we can get this. A simple harmonic oscillator has a period that is independent of the amplitude. The period is independent of the amplitude for an oscillating mass. You have you know that already. If you have a pendulum, if you swing it from a greater displacement or a smaller displacement, the period of oscillation is the same. A greater amplitude means that the oscillator has to travel a greater distance in the same time, hence it has a greater speed. Now since the period is the same, because it has to have the same period even if it is displaced from a greater distance, if the oscillating mass, it has to have a greater speed. That is shown by this: greater the amplitude, greater the speed. The equation also shows that v0 is proportional to the angular frequency. So this is the maximum velocity is proportional to the angular frequency. So that maximum speed is proportional to the, okay, so omega is angular frequency. Increasing, now frequency they say in short, but it is the angular frequency because we use f for frequency. Okay, anyway, increasing the frequency means a shorter period. A given distance is covered in a shorter time. Have another look at figure 19.15. The period of the motion is 0.4 seconds and the amplitude of the motion is 0.02 meters. The frequency can be calculated as 2.5. Now figure 19.15, we looked at it again and again. Yeah, so you can see period is 0.4, amplitude is 0.02. Okay, so then we get the frequency 2.5 Hertz. page 296, right? Okay, so we can use the equation v naught is equal to 2 pi f x naught, because v naught is omega x naught, this equation, this one, that is when the displacement is 0, where you get the maximum velocity. Okay, you get the maximum velocity when the displacement is 0, so that's how you get this equation. Then f equation, this thing, to determine the maximum speed v naught. Now we already know what f is. Okay, we calculated it over here. Okay, period is constant, so the frequency is also constant, but this is the just frequency, okay, not the angular frequency, so don't confuse the two. Over here they just call it frequency, but that is the angular frequency. Here it is the just the frequency. Okay, so period is constant, so the frequency here is constant. Now we have we substitute in here all those quantities and we get 0.31. Okay, this is how the values of figure 19.1b were calculated. So using this equation, now you know that the velocity can be calculated. Okay, I was talking about it earlier. You can find the gradient of the graph, I said, or there is another way, so you can use this equation. See, 0.30. So even for the questions without drawing the tangent, you can find the maximum velocity using this equation. So if you know the frequency, if you know the maximum displacement, you can find the maximum velocity using this equation. But at that time you didn't learn this equation, now only you learned this. So what you can do is you can apply this equation now for those questions where you had a displacement type graph and you had to find the maximum velocity. Now you can apply it and find whether you get the exact answer. Okay, so this is also an important equation. Okay, v naught is equal to omega x naught, you have to remember that also. Then 2 pi f, you can use that. Okay, so we'll see the derivation of these equations for velocity and acceleration from the equation for displacement if we start timing when the displacement is 0. So when the time is 0, the displacement is 0. Okay, so therefore we get a sine graph for the displacement versus time graph for the simple harmonic motion. Then we differentiate this. Okay, those students who have taken mathematics will already be familiar with this. When you differentiate sine, you get cosine, and remember the inside also has to be differentiated and multiplied by the result of that differentiation. Since we are differentiating with respect to time, all the others are constants. Okay, so we are getting the first derivative of this dx over dt, change in the displacement divided by time, that is velocity. Then sine, when you differentiate you get cosine, then the inside part also differentiate, you get omega and multiplied by what is outside, so you get x naught omega cosine omega t, x naught omega cosine omega t, that is the velocity. Now I have put this inside this yellow border because we know v naught, we have learned previously that v naught is equal to omega x naught. Okay, so v naught equals omega x naught, I wrote it here. So the same thing we have here, so we can replace the x naught omega with v naught, so v naught cosine omega t. Then acceleration is the second derivative of displacement, or when you differentiate this you get acceleration. When you differentiate velocity with respect to time, you get acceleration. Then d2x over dt squared, d squared x over dt squared. When you differentiate this, you will get this. Okay, cosine, when you differentiate you get minus sine, I put the negative sign over there, and when you differentiate the inside you will get again an omega, that omega multiplies by what is here, then you get omega squared. Okay, so unlike what I said previously today in the explanation, there is an omega that is coming out and that multiplies by whatever is outside. and we know that this part here, which I have in the yellow border, which is inside that yellow border, that is the same as this, x naught sine omega t, x naught sine omega t. So I can replace this part with x, then we have this x. So acceleration is minus omega squared x. Now we saw this equation earlier. See, acceleration is minus omega squared x, which is what we have here. So that's it for the derivation. This one I haven't shown. You should memorize this equation. Okay, let's move on then. The next topic is energy changes in simple harmonic motion. During simple harmonic motion, there is an energy change. For example, over here, the energy changes from kinetic energy to gravitational potential energy. So there's a constant interchange of energy between two forms, potential and kinetic. We can see this by considering the spring mass system shown in figure 19.21. So here, elastic potential energy converts to kinetic energy, and kinetic energy converts to elastic potential energy, also called strain energy. So at this end, it has maximum elastic potential energy and kinetic energy is 0. Then what happens? That elastic potential energy converts to kinetic energy, and when it is at the equilibrium position, if the springs are neither compressed nor extended, then the elastic potential energy is 0, kinetic energy is maximum. Kinetic energy, it has students must decrease. Okay, so we assume there are no heat losses due to friction. So we assume that there is perfect conversion between kinetic and potential energies. The energy is not converted to any other form such as heat or sound. Okay. So no friction, so oscillations are undamped, because if there was friction, then what will happen is the amplitude of oscillation decreases with time. So if it is undamped, then the total energy remains constant, because potential energy plus the kinetic energy is a constant. Okay, so we will get a graph like this. You can see that over here, the potential energy converts to kinetic energy converts to potential energy. So whatever decrease in potential energy is equal to the increase in kinetic energy. Similarly, whatever decrease in kinetic energy is equal to increase in potential energy. So the sum of kinetic and potential energies is the same throughout the motion if there is no damping, if there is no energy losses to any other forms such as energy loss due to friction, which is heat. Okay, now you can also see one whole cycle. So from here all the way to here, that is one whole cycle. Let's say we start at the equilibrium position. The kinetic energy at the equilibrium position, which is at the center of the oscillation, is maximum. Potential energy is 0. Okay, so here they are not starting at the equilibrium position, they are starting at the extreme position, because kinetic energy is 0. At the extreme ends, the kinetic energy is 0. Okay, so what happens is, now let's say we start here, then the kinetic energy increases and becomes maximum, which is at the equilibrium position. So imagine we start at the far right end, then it's moving to the left now. Okay, so it moves to the left and it comes to the equilibrium position. So kinetic energy is maximum. Then from the equilibrium position, it moves to the far left end. Okay, that is over there. So again the kinetic energy becomes 0, because it comes to a momentary stop at the far extreme end, left end now. Then what happens? Again it moves to the equilibrium position from the left to the middle. Then kinetic energy is maximum, and then from the middle to the far right end, that is over there. Now over there again the kinetic energy is 0. So you can see that is one whole cycle. We started at the far right end and we ended over here at the far right end again. Note that both kinetic and potential energies go through two complete cycles during one period. So so one period means one complete oscillation. You can see 1, 2 cycles for kinetic energy, and also 1, 2 cycles for potential energy. That's what they mean by this. This is because kinetic energy is maximum when the mass is passing through the equilibrium position, moving to the left and again moving to the right. So there are 2 points where the kinetic energy is maximum, that is at the equilibrium position. 2 points means it is maximum at the equilibrium position. So this passes through the equilibrium position twice. That's why the kinetic energy is maximum there. This is because kinetic maximum when the mass is passing through, moving through left and moving to the right again. The potential energy is maximum at both ends of the oscillation. Potential energy is maximum at both ends of the oscillation. That is at the 2 extreme ends. It comes to a momentary stop. So all the kinetic energy there has converted to potential energy. Okay, so we can see total energy is constant if the system is undamped. All right, then these questions I will leave it for you all to answer because it is time consuming to do these questions. Okay, very simple. Use the equations that you have learned. You can have all the equations written down. Then it will be easier for you to figure out which equation you are supposed to use for the question. And if any doubts, let me know. We can discuss those questions. Okay, then the next part. Okay, a second way to show this is to draw a graph of how potential energy and kinetic energy vary with displacement. See, when the potential energy decreases, the kinetic energy increases by the amount that the potential energy decreased by. So therefore always, if you look at this in the vertical direction, the sum of kinetic and potential energies is a constant. That is means the total energy is constant. Potential energy is maximum at both ends of the oscillation. Then we went through that already. So kinetic energy is maximum when the displacement is 0. Potential energy is maximum when the displacement is equal to the amplitude, that is at maximum displacement. At any point on this graph, the total energy, which is kinetic energy plus potential energy, has the same value. The kinetic energy is maximum at 0 displacement. Okay, kinetic energy is maximum at 0 displacement, and potentially maximum at maximum displacement. Okay, so I already explained this. So maximum displacement is at x plus x naught and minus x naught. Okay, so you have to answer all these questions. Now this is about damping, the next topic. Alright, I have already explained what damping is. Now why this occurs? That is because the energy is converted to heat energy due to friction. Now if there was no friction, the amplitude will remain the same. But because the friction transfers energy away from the system, the amplitude of the system decreases and eventually becomes 0. So we call this, the oscillations are damped and their amplitude decreases according to a particular pattern like this. Here we call this the exponential envelope. This is displacement versus time graph. The oscillations are damped. Alright, in the glossary, the meaning of the word damped is given. Describe an oscillatory motion in which the amplitude decreases with time due to energy losses. So here is the definition. Already I have explained this to you. So it has to be an oscillatory motion in which the amplitude decreases with time due to energy losses. Alright, so about the way this amplitude decreases, we have an exponential envelope. You can see the amplitude of damped oscillations does not decrease linearly, it decreases exponentially with time. See, exponential envelope. An exponential decay is a particular mathematical pattern that arises as follows. At first, the swing moves rapidly. There is a lot of air resistance to overcome, so the swing loses energy quickly and its amplitude decreases at a high rate. Later, it is moving more slowly. There is less air resistance and so energy is lost more slowly. So you see, later it is moving more slowly, so energy is lost more slowly. Now you can see that happening over here. Okay, so in the beginning there is a big decrease, and then with time the decrease doesn't decrease that drastically. In the beginning this decrease in amplitude is drastic, but when the amplitude decreases, it decreases at a slower and slower rate. That's what they mean by this. There is a lot of air resistance to overcome, so the swing loses energy quickly and its amplitude decreases at a high rate. Later it is moving slowly, there is less air resistance. You know, air resistance decreases with decreasing speed, and so energy is lost more slowly. The amplitude decreases at a lower rate. Hence we get the characteristic curved shape, which is the envelope of the graph in figure 19.25. Notice that the frequency of the oscillations does not change as the amplitude decreases. Frequency of the oscillations does not change. See, the period is the same. The time for one complete oscillation is the same, or we can say the number of oscillations per second is the same. Frequency is the same. If frequency is the same, period is the same. This is a characteristic of simple harmonic motion. The child may, for example, swing back and forth once every 2 seconds, and this stays the same whether the amplitude is large or small. Previously also I explained this. The period or frequency is independent of the amplitude of oscillation for a particular system. So even if you give it a small displacement, if you start swinging it from a small displacement or a large displacement, the period of oscillation will be the same. Now this is to investigate damping. So you can see what happens. You can see over here they have fixed it, the hacksaw blade, to this mass, maybe using blue tack. Have hacksaw blade to this card, okay, to the card, and then there is something to, like a blue tack or something, to fix it to that mass. Hacksaw blade, and then this ruler is used to measure the displacement or the amplitude, and you will notice that with time it decreases like this. Okay, very easy. You can investigate the exponential decrease in the amplitude of oscillations using a simple laboratory arrangement. A hacksaw blade or other springy metal strip is clamped vertically or horizontally to the bench. A mass is attached to the free end. Now see, this ruler is not hanging on there, it's fixed to the wall. You can see, using the tape, the ruler is fixed to the wall. You are not just holding it like this with your hand. It has to be fixed. Okay, so here we have a mass, then we have a card. Now this card is there to increase the damping. If this card was not there, it will take a longer time for it to stop swinging. But when the card is there, the bigger the card, the greater will be the air resistance, so greater will be the damping. See, a card is attached to the mass so that there is significant air resistance as the mass oscillates. The amplitude of oscillation decreases and can be measured every 5 oscillations. So every 5 oscillations, measure the amplitude by judging the position of the blade against a ruler fixed alongside. So that's why I said, when you are drawing apparatus, don't draw it hanging, or not hanging, rather floating. You have to attach it like this. A graph of amplitude against time is shown, will show the characteristic exponential decrease. You can find the half-life of this exponential decay graph by determining the time t it takes to decrease to half its initial amplitude. So here is the initial amplitude, half the initial amplitude. The time is 1 half-life for the decrease in amplitude by half. And you can see I told you before, by changing the size of the card, it is possible to change the degree of damping and hence alter the half-life of the motion. Now if you have a larger card with a larger surface area, the R resistance will be more. A typical graph of amplitude against time for damped oscillations, amplitude versus time. Okay, then energy and damping. Damping can be very useful if you want to get rid of vibrations. For example, a car has springs. Now you can see that over here. You have to understand that this is used in vehicles, and a lot of students confuse the shock absorbers with the springs or dampers. Okay, the springs and shock absorbers in a car suspension system form a damped system. Okay, so actually this is the damper, this is the spring, which is the shock absorber. Okay, I think even in this book it is not explained clearly. Okay, but the same thing is in another book in your actually not your one, in another syllabus, same picture is there. The students at overseas school use that book, and in there it is clearly explained that it is an American syllabus. Okay, this is the British syllabus we are doing. Okay, damping can be very useful if you want to get rid of vibrations. For example, a car has springs which make the ride much more comfortable for us when the car goes over a bump. However, we wouldn't want to suspend every car journey. Sorry, we don't want to spend every car journey vibrating up and down as a reminder of the last bump we went over. So the springs are damped by the shock absorbers. Yeah, so here also it is not explained correctly. See, they identify the springs, they identify this as the shock absorber. This is not the shock absorber, the spring is the shock absorber. And we return rapidly to a smooth ride after every bump. Now you would have seen this in certain restaurants and hotels. This is also fixed to the top of the door. So when you open the door doesn't close suddenly. It closes slowly because of the damper. Okay, the spring is the shock absorber. This part here is the damper. Okay, see, damping is achieved by introducing the force of friction into a mechanical system. In an undamped oscillation, the total energy of the oscillation remains constant. So if this damper was not there and if there was no friction, when the car goes over a bump, it will continue to oscillate up and down. Okay, so this is what they are explaining. There is regular interchange between potential and kinetic energy. By introducing friction, damping has the effect of removing energy from the oscillating system, and the amplitude and maximum speed of the oscillation decreases. Okay, I think there was a graph with over damping, under damping. Yeah, that is this one. Okay, so we will learn about that after resonance, and we will compare everything together. Okay, so resonance is also a very important topic. See, important physical phenomena that can appear in many great different situations. Yeah, so what happens is resonance occurs when the driving frequency is equal to the natural frequency of the object. At that point, the object will oscillate with maximum amplitude. Then we call this effect resonance. So something like that happened here in this bridge, where about 2000 pedestrians walking on the bridge started to sway dangerously. People also swayed in time with the bridge. Now this is an example, like, you know, in the beginning I gave you the example of the swing. Let's say there is a child on the swing, and then you want to have the child swing with a greater amplitude. So what you do is you match the natural frequency of oscillation of the swing. So if you release the child, the swing will naturally oscillate at a certain frequency. So when you are pulling the child, you have to match that frequency. So when the swing is moving back, you also move back with the swing, and then when it's moving forward, you also move forward. And this, when you do this, what will happen is the swing will swing with a maximum amplitude. Okay, so something similarly happened here in this bridge. Okay, when people were walking, the bridge started swinging, so the people also started swinging with the bridge in the same way the bridge was swinging. So they swayed in time with the bridge, and this caused the amplitude of the bridge's oscillation to increase. So then you get resonance. Now when that happens, it will vibrate with maximum amplitude, and as a result the bridge can break or get damaged. Okay, then eventually they fixed it. They added dampers so that this will not happen. Okay, so the dampers absorb the energy of the oscillations. Dampers to the bridge to absorb the energy. Actually it's the spring, I think, over here that is absorbing the energy, but anyway, the bridge was then reopened, and then okay, so this is the example of the swing. Okay, I have already explained that. And here we have what we call the Barton's pendulum. Okay, so what you do is you swing this, you pull it towards you and release it. Then what will happen, this will start swinging like this. Then what will happen is, now these are of different lengths, but you know the period of a pendulum, t is equal to 2 pi square root of L over G. That is the equation for period of a pendulum. So period of a pendulum depends on the length of the pendulum. Now you can see this pendulum and this one over here has the same length, approximately the same length. So therefore the period of this pendulum and the period of this pendulum, the natural frequency, the period or natural frequency will be the same, because the period t is equal to 2 pi square root of L over G. That is the period of a pendulum. Period of a pendulum depends on the length. So if the lengths of the pendulums are the same, it doesn't matter what the mass here is, okay, then they will have the same natural frequency of swinging, that is oscillation. Now you can see when you swing this, what will happen, it will cause this also to swing. Okay, it will cause this also to swing, but you will see that this is the driving frequency or forced frequency. This is causing these to swing. So here they are forced to oscillate. So this is the driving frequency, and then these are forced to oscillate. Now you know that when the natural frequency is equal to the driving frequency, it will oscillate with maximum amplitude. So what will happen is, you will notice that this one here, because it has the same length as this one, this will oscillate with maximum amplitude. So these other pendulums will not, these others will not oscillate with maximum amplitude, but the one which is having the same length will oscillate with maximum amplitude, because it has the natural frequency which is equal to the driving frequency of this. Now this is also oscillating naturally, but when it is oscillating naturally, it is causing the others to oscillate. So this oscillation is equal to the natural frequency of this one, so therefore this will also oscillate with maximum amplitude. Okay, so here you see driver pendulum, that is this one. However, only the pendulum whose length matches that of the driver pendulum builds up a large amplitude so that it is resonating. So when the natural frequency is equal to the driving frequency, it will oscillate with maximum amplitude. We call that resonance. Okay, so here also you can see resonance with the spring mass system. Okay, in here what happens is, you can observe resonance for yourself with a simple spring mass system. You need a mass on the end of a spring chosen so that the mass oscillates up and down with a natural frequency of about 1 Hz. Now hold the top end of the spring and move your hand up and down rapidly with an amplitude of a centimeter or two. Very little happens. Now move your hand up and down more slowly, close to 1 Hz. you should see that the mass oscillating with gradually increasing amplitude. Adjust your movement so that the exact frequency of the natural vibrations of the mass, and you will see the greatest. So what happens is, you can move your hand up and down until you come to a point where it equals the natural frequency. When that happens, this will oscillate up and down with the maximum amplitude. So there you get resonance. Now even the example of the swing is given here. Okay, if you were to push the child quarters of a swing, you would soon find that the swing was moving backwards as you try to push it forwards. Okay, so if you didn't match the natural frequency when you are swinging a child on the swing, the swing will stop swinging. But if you match it, you can make the child go with the maximum amplitude on the swing. Okay, so again, this word resonance is important. Okay, in the glossary, we have the meaning of the word resonance: the forced motion of an oscillator characterized by maximum amplitude when the forcing frequency matches the oscillator's natural frequency. So the forced frequency matches the oscillator's natural frequency. A system absorbs maximum energy from a source when the source frequency is equal to the natural frequency of the system. So this is where we get resonance. We get maximum amplitude when the forced frequency is equal to the natural frequency of the object, and at that time the system absorbs maximum energy from the source or the object that is causing it to oscillate. Okay, so therefore it oscillates with maximum amplitude, and that point we call we have resonance. Okay, so back to the chapter, we can see here, when the forcing frequency matches the natural frequency of the system, the amplitude of the oscillations grow dramatically. So this is what you should know. Okay, here are the points again. The following statements apply to any system in resonance. Its natural frequency is equal to the frequency of the driver. Frequency of the driver means the frequency of the object that is causing it to oscillate. Okay, so if the natural frequency of the object that is oscillating is equal to the frequency of the object that is oscillating it, then its amplitude gets maximum. It absorbs the greatest possible energy from the driver or the body that is oscillating it. Okay, and if the driving frequency does not quite match the natural frequency, the amplitude of the oscillations will increase, but not to the same extent as when resonance is achieved. Figure 19.32 shows how the amplitude of the oscillations depends on the driving frequency. In resonance, energy is transferred from the driver to the resonating system more efficiently when resonance does not occur. Than when resonance does not occur. Okay, so when resonance occurs, you get the maximum. Yeah. So when resonance occurs, you get the energy transferring very well. Okay, you should know this graph. Okay, in the exam papers, I have seen this being questioned. You have to draw it. So amplitude, here we have driving frequency. So when the driving frequency equals the natural frequency of the object that is oscillating, then you get the object oscillating with maximum amplitude. So at this point we have resonance. Maximum amplitude is achieved when the driving frequency matches the natural frequency of the oscillation. Okay, so this graph is also important. Now you can see if the building is not built in a way that it can withstand these earthquakes, that means by fixing dampers into that building, the building will collapse. But if the dampers are fixed, what will happen is that amplitude of oscillation is reduced. You can see over here the black curve is used to indicate heavier damping. Here blue line is used to indicate light damping. Now let's say we have this kind of original graph which is in green without damping. Okay, so damping reduces the amplitude of resonant vibrations. So what happens is, the more you damp it, the lesser will be the amplitude of oscillation for example during an earthquake. Now during an earthquake, what happens is the earthquake is causing the building to vibrate. So if the frequency of vibration of the earthquake is equal to the natural frequency of the building will absorb maximum energy from the earthquake and it will vibrate with maximum amplitude. This can cause the building to collapse. But if there are dampers fixed to the building, it will reduce that amplitude of oscillation and prevent the building from collapsing. Few more points about this. In addition to the amplitude decreasing, the curve becomes broader. You can see the resonance peak becomes broader. This is the resonance peak, it becomes broader. So notice that. Now this is very important over here. I will show it like this. Notice that as the degree of damping is increased, the amplitude of the resonant vibrations decrease. The amplitude decreases. You can clearly see that the resonance peak becomes broader. Okay, you can see it's broader. Now here the tip is sharper. Here it's not as sharp. Can you see it's broader? Here also it's even more broader. The resonance peak becomes broader. There is also an effect on the frequency at which resonance occurs. Can you see this tip of the curve is moving to the left? Okay, so that means the frequency also decreases. There is also an effect on the frequency at which resonance occurs, which becomes lower as the damping increases. So 3 points here. When you increase damping, or the amplitude decreases, the curve becomes broader and the frequency, resonance frequency decreases. So keep those three in mind. Okay, they can test this in the exam papers. I have seen this kind of graph being asked and they ask you what is happening, or they ask you to explain it, or they ask you these 3 points. Damping reduces amplitude of resonant vibrations. So 3 points again. The amplitude of resonant vibrations decrease, the resonance peak becomes broader, and the resonance frequency becomes lower. Okay, as the damping increases, this happens. Alright, then this is also a very important graph. Okay, like I said, this graph is very important. We can explain this using an example of the restaurant door. Okay, for example, a restaurant may have a door leading to the kitchen. Now if it is if it is underdamped, what will happen is the door will swing back and forth for a long time before it stops or closes. But if it is overdamped, what will happen is once the door is open, it will take a long time for the door to close. But if it is critically damped, then what happens is after somebody opens the door will close at the right speed at the right time. Okay, so that's what is explained over here. For example, a restaurant may have a door leading to the kitchen. This door can swing open in either direction. Such a door is designed to close by itself after someone has passed through it. Ideally, the door should swing back quickly without overshooting its closed position. To achieve this, the door's hinges or the closing mechanism must be correctly damped. If the hinges are damped too tightly, the door will swing back and forth several times as it closes. Okay, so that is underdamped. Okay, if the damping is too heavy, here damped too lightly. Okay, so here there is underdamping. What we saw, it will swing back and forth a long time before it closes. If the damping is too heavy, it will take too long to close. So that is overdamping. See, it takes a long time for the door to close. So this is amplitude, this is time. Okay, so here you see in underdamping the amplitude goes positive, negative, positive, negative. That means this door can open both ways. Okay, in a restaurant the door can open both ways. So if it is underdamped, it will go back for open one way, it goes to the other side, it will take a long time. But if it is overdamped, it will take a long time to close. But if it is critically damped, it will close at the right speed at the right time. Okay, so with critical damping, the door will swing closed quickly without oscillating. Critical damping is thus the minimum amount of damping required to return an oscillator to its equilibrium position without oscillating. So minimum damping required to return an oscillator to its equilibrium position without oscillating. You can see this word here, critical damping, is in green bold letters, which means you should know the meaning. Okay, so this is an example where you can use it for a door. Similarly, you can use this graph for the example of a vehicle, let's say a double cab. Okay, you know, if you consider a SUV, if it is under damped, what will happen is once the SUV goes over a pothole, it will go up and down for a long time until it comes to the normal horizontal position. But if it is under damped, sorry, if it's over damped, then the people inside the vehicle will feel the shock. It will be uncomfortable. Okay, because once it goes over a pothole, it takes a longer time for it to come to the horizontal position. But if it is critically damped, once it goes over a pothole, it will come to the horizontal position at the right time, at the right speed, so that the passengers don't feel uncomfortable. Okay, you see, so under damping results in unwanted oscillations, over damping results in slower return to equilibrium. The car's suspension system uses springs to smooth out bumps in the road. It is usually critically damped so that the passengers do not experience nasty vibrations every time the car goes over a bump. Critical damping is just enough to ensure that a damped system returns to equilibrium without oscillating. Okay, then we have some uses of resonance. Okay, here are some uses again. We use resonance in the microwave. Okay, so those microwaves have a frequency that is matching the natural frequency of the water molecules. And what happens is when those microwaves reach the water molecules, it causes the water molecules to vibrate. And since the frequency of the microwaves matches the frequency of the water molecules will vibrate with maximum amplitude. This causes the food to heat up. The food that is put inside the microwave heats up this way. Okay, so resonance is not confined to mechanical systems. It is made use of in, for example, microwave cooking. The microwaves used have a frequency that matches the natural frequency of vibration of water molecules. The microwave is the driver and the molecule is the resonating system. So the microwave causes the water molecules to vibrate. That is why the microwave is the driver and the water molecule is the resonating system. So remember these two words, driver and resonating system. The water molecules in the food are forced to vibrate and they absorb the energy of the microwave radiation. The water gets hotter and the absorbed energy spreads through the food and cooks or heats it. So remember, this is one use. There are more uses over here. Another one is magnetic resonance imaging. In short, we call it MRI. You know, MRI scans is increasingly used in medicine to produce images such as in figure 19.36. Okay, you can see that here. This magnetic resonance imaging MRI picture shows a man, a woman and a 9-year-old child. The image has been colored to show up bones, white, lungs, dark and other organs. So here also we are using resonance. Now previously we saw some disadvantages of resonance. Okay, now here are some uses of resonance. Radio waves have a range of frequencies. Having a range of frequencies are used and particular frequencies are absorbed by particular atomic nuclei. The frequency absorbed depends on the type of nucleus and on its surroundings. By analyzing the absorption of radio waves, a computer-generated image can be produced. There is much more about how MRI works in chapter 32. Okay, I think that chapter is under medical imaging. Okay, we can quickly have a look over here. Chapter 32, yes, medical imaging. A radio or television also depends on resonance. So, so far we learned two advantages. One is in the microwave and the other one is for MRI. And here is another example. A radio or television also depends on resonance for its tuning circuitry. The aerials pick up signals of many different frequencies from many transmitters. The tuner can adjust to resonate at the frequency of the transmitting station you are interested in, and the circuit produces a large amplitude signal for this frequency only. So this way you can hear the station that you want to. Okay, so what happens is you adjust the tuner so that it resonates at the frequency of the transmitting station that you want to listen to. This way you can listen to that particular station. Okay, so finally, big ideas in physics. This study of simple harmonic motion illustrates some important aspects of physics. Physicists often take a complex problem such as how the atoms in a solid vibrate and reduce it to simpler, more manageable problem such as how a spring mass system vibrates. This is simpler because we know the spring obeys Hooke's law, so that its force is proportional to the displacement. Okay, so about the equations over here, they are explaining sine and cosine equations we have considered above. Okay, so here they are explaining about the analogy. Spring mass system also works well for vibrating atoms and molecules, for objects bobbing up and down in water, and in many other situations. Okay, so modifying the theory, a theory to fit a greater range of situations. For example, what happens if the vibrating mass experiences a frictional force as it oscillates? Then we get damping, as discussed above. And if the spring does not obey Hooke's law, this is a harder question to answer. Okay, so big ideas in physics, and we have come towards the end of this chapter on simple harmonic motion and oscillations. Here is the summary. The summary is also very important because it's kind of like a review of what you learned. Okay, so let's go through the summary. Many systems, mechanical and otherwise, will oscillate freely when undisturbed from their equilibrium position. Some oscillators have motion described as simple harmonic, SHM, simple harmonic motion. For these systems, graphs of displacement, velocity and acceleration against time are sinusoidal curves. So even this we call it sinusoidal. Even though it's a cosine graph, the shape is this way, like a sine graph. So all three are sinusoidal. So even cosine graph is called sinusoidal curve. Okay, shape is sinusoidal. So here we have displacement time, and you know from the gradient you can get the velocity time graph, and the gradient for this you can get the acceleration time graph. And you can see they have drawn these vertical lines to indicate what happens. Here the gradient is 0, so the velocity should be 0 here. Here the gradient for this graph is maximum, so acceleration should be maximum. Over here the displacement is 0, but the gradient is maximum, so velocity is maximum, but the gradient is negative, so the velocity is maximum negative. And over here the gradient is 0, that means the acceleration should be 0. So you can go along a line and see what happens. Over here gradient is 0, that means velocity is 0. Over here gradient is maximum, positive, so acceleration is maximum and positive. Okay, so during a single cycle of simple harmonic motion, the phase changes by 2 pi radians. So if the angular frequency omega of the motion is related to its period t and frequency f, omega equals 2 pi f. So 2 pi for 1, so if there are f number, then 2 pi f. We saw this earlier when we were learning about angular frequency. Okay, one more thing. Okay, so first we'll go through this part. In simple harmonic motion, displacement x and velocity we can be represented as functions of time t by equations of the form x equals x naught sine omega t, v equals v naught cosine omega t. I showed you the derivation also earlier. This one. A body executes simple harmonic motion if its acceleration is directly proportional to its displacement from its equilibrium position and is always directed towards the equilibrium position. So when you should know the definition of simple harmonic motion, and I also explained this in detail at that time. Acceleration a in simple harmonic motion is related to displacement x by the equation, this one. The maximum speed v naught in simple harmonic motion is given by the equation v naught equals omega x naught. V naught equals omega x naught. Okay, that equation also we saw it here, and you have to be able to do questions involving all these equations. The frequency of or period of a simple harmonic oscillator is independent of its amplitude. Already explained. In simple harmonic motion, there is a regular interchange between kinetic energy and potential energy. Resistive forces remove energy from an oscillating system. This is known as damping. Damping causes the amplitude to decay with time. Then critical damping is the minimum amount of damping required to return an oscillator to its equilibrium position without oscillating. Very important definition of critical damping. Next point. When an oscillating system is forced to vibrate close to its natural frequency, the amplitude of vibration increases rapidly. The amplitude is maximum when the forcing frequency matches the natural frequency of the system. This is resonance. So again, very important. Make sure you study this, because in paper 4 they can ask you to write this. What is resonance? What is critical damping? Resonance can be a problem, but it can also be useful. We saw some uses of resonance, for example MRI in the microwave, and also radio or television. Okay, signals, to pick up the signals, okay, in its tuning circuitry. And we saw some disadvantages, like for example in the case of buildings that are built in earthquake areas, the bridge, okay. And also we talked about vehicles and how we can prevent this using dampers for all three cases. Alright, so that is the end of that chapter. Now make sure you do all the questions. We didn't go through these questions in the brown boxes. The beginning, the questions that were in the beginning we already discussed, but here we didn't discuss any of these questions. So make sure you go through and do all these questions. Check the answers. Here in this page also there are a lot of questions, but I don't think it will take a long time. Only thing is you have to use the equations, substitute, and then get the answer. Okay, so make sure you do all these questions, and after you finish that you can start doing the questions at the end of the chapter, the end of chapter questions, okay, which is after the summary. And you can also do the questions on the drive and the questions in the past paper books. So first thing is finish all the questions in the brown boxes, then you can start doing the questions in the past paper books that has the solutions. Then you do the questions in the drive. While you do the questions in the drive, you can do these questions also. Even while you do the past paper questions in the books that I gave you with the solutions, you can start doing these questions. These are also kind of like past paper questions. I think they have taken this from the past papers. Okay, so that's the end of the chapter Oscillations, which is also the chapter on simple harmonic motion.